What's going on, everyone? Good morning, afternoon, evening. Welcome back, everyone, to SOC100 stream over here at Level Effect. Good to see everyone here today. Got a good-sized crew in the morning. Looks like about 20 of us over here in chat. Not bad, not bad. Jacopo's here, Ariel, Bearded, Vinny, Alan, Karina, Kim, KS, Doug's here, and TomTom's here as well too. Cool. All right. Good stuff. Great time last night in the voice channel, Karina and KS. I saw you guys. I saw you hanging out in the SOC100 channel. Yeah, I saw that. Saw y'all hanging out. You went pretty late too. By the time I went to bed, and then I was looking back on the channel, just kind of see if there's anything like urgent, whatever, popping up. I saw you guys were like hanging out till like close to midnight. Not bad. You went till 2 a.m. and you're showing up to class at 10 a.m. Look at that. That is some dedication. That's some perseverance. Not bad. Well, make sure you get some rest too. So what were you studying? Cryptography? You have your exam soon. This would be your review. Yeah, cool. Ariel needs a cool cyber username as well too. I saw that up in chat. So we need to figure out something for Ariel. Well, I think so I think Karina, KS, and Bearded, I think the only reasonable thing to do now is I think we're gonna have to have all three of you come on stream and do a little presentation on what it was that you were all cooking up last night until 2 a.m. That's what I think. That is what I think we need to do. Need to get you up and on here. Yeah, Spartacus, the stream was recorded yesterday, so it takes me like I basically put like a backlog, so I get all the streams and everything edited and rendered and cut and uploaded to YouTube and all that stuff. Starting on the Monday. So Monday, Tuesday, Wednesday. So Monday will be Doug's recording. Tuesday will be the SOC is today's stream. Wednesday will be tomorrow's stream. So I do like a lead from the Monday onwards of however much we streamed. But yeah, I mean, we're not going to do SOC100 forever, and I'm definitely going to be pulling some more alumni and community members up on stream as soon as we get through all this, so get ready. But cool, yeah, good work. Burn the midnight oil. So today is more cryptography, so we actually need to continue that. We're going to do a little bit of a walkthrough of the entire TCP TLS kind of process, right? We're going to look at the handshake, we're going to look at the key exchange, and the subsequent symmetric encryption that happens thereafter. And then we're going to do some labs. So then we're actually going to do some encryption ourselves. We're going to do some hashing, some encoding, some symmetric, some asymmetric, and we're going to look at digital certificates today as well too. And what else? And then I think we're going to have some time as well to go into the Windows module. We're going to kick that off, and we're going to do a lecture on processes, threads, programs, a variety of things, kind of talking about that, components of a process and such. And then I think we're going to pull up Process Explorer on the SysNturtles kit. So we got a pretty big day ahead of us. So for those of you that partied until 2 a.m. studying, hope you get some extra coffee today. We actually have a lot to cover. It's a pretty big day. Aside from that, though, how's everyone doing in general? Did y'all enjoy Doug's stream yesterday? I thought it was awesome. What'd you guys think? Yeah, pretty good. Looks like you had some time for the stream as well. Yeah. Ariel, when you caught it, it was a little overhead, but you're at home with 4 kids. Yeah, that would be, that would do it. That's a lot of additional bandwidth. R double, yeah, it was awesome. Yeah, it was a nice teaser, right? Like, for those of you that are still kind of newer in the ranks, Zeno, you thought it was awesome, but had to watch recording because working had a crazy snowy ride home down the mountain. Cool. Sounds fun. Yakbo thought it was awesome as well. You'd like to dive deeper in examples such as Metasploiter topics as suggested by Doug with them. Nice, yeah. Absolutely. Well, okay, the good news is this. Listen. The next time you start seeing more and more of that content, it's just going to make more and more sense. And that's a teaser of where you're going to be able to be. If you just keep at this, you keep attending these streams, you keep doing the work, you keep staying engaged. In a couple months, several months from now, you're going to be able to do that kind of stuff and look at it and analyze it and think about it and be able to talk about it. And honestly, that's a pretty encouraging thought, in my opinion. Maybe I'm the only one encouraged by that. No response, no comments. I'm just gonna assume or hope you're encouraged by it, okay? By me saying that. Nice. Okay, cool. Well, yeah, maybe I've had more coffee than all of you so far. Maybe that's what it is, or maybe I wasn't up so late. Drink coffee will enable the encouragement. Area. Yeah, I know, Doug. Like, they're just completely broken with that comment. Day 47 asking for your black level effect mug. Yeah, KS, it's almost there. Too early for Zeno. Ariel, nice. Congratulations. You got the job offer, Associate SOC Analyst. Amazing. Well done. That's awesome. Very, very good to hear. Yeah, it's huge. I love hearing that. You know, just seeing students kind of keeping at it, applying themselves, and then landing what they're looking for. Yeah. Ariel's even more motivated to come to class. Yeah, nice. Yeah. Yeah, I mean, I hope that you can start, like, once you start, I hope that you can apply the things that you're learning here, and I'd love to hear that. Like, I'd love to hear what has helped you from the program, and for anyone, like anyone that's getting a job and stuff, I'd really like to hear if the course has helped you and what you've been able to apply, and also bring your thoughts. You know, like bring your thoughts to the stream, bring your thoughts and experience to Discord. And like I said earlier on, I'm definitely going to want to start picking at the community of, well, who wants to hop on stage and just do maybe like a 30, 45 minute kind of demo of something. So kind of want the whole full circle to go around. But amazing, Ariel. Congrats again. You've been working hard too at this, so it's definitely paid off. Cool. Yeah, nice, Doug. Thanks for hopping in there with Ariel. If you guys can do a little chat. MSSP is going to be really good. Really, really good experience for you. My first major technical role was at an MSP. There was some security to it. It was more so IT, but there was definitely some security to it. And probably more actually now that I think about it when I look back on it. Because there's so much overlap. But anyways, you're going to learn a ton in that type of environment. There's so much exposure. Like rapid experience, rapid growth. So it'll really expedite your time that you're investing into it. Beard will be starting soon in SOC. Homie's putting in the work. Yeah. Yeah, it's awesome. Let's get every single one of you working in this field. That'd be amazing. I want to see that. That's right, winning in life. Yeah, but seriously, I definitely want to pull some of you on and kind of like a fireside kind of chat, casual, the human behind what's going on, like raw takes and experience of like what it's like, sharing your thoughts and your perspective and your insight. So that's gonna be something we're gonna be cooking up soon as we start to kind of reel off. So on that note. Okay, so on that note, like SOC 100 stream calendar, right? We're around here, and it's about a month away when we're having like, excuse me, a little dry this morning, cold weather, but until around like mid-February is when we're going to be having like the bulk of the work. So it's been since October to February, effectively, of just like learning and going through everything. SOC 100-3 and 4 is a lot of just like you. It's just like you doing the work kind of thing. So they're really, the classes aren't like classes. In fact, there's going to be 3 days of no class for that. And then afterwards, with SOC 100-5, it's a lot of like guest instructors coming in and then walking through some more advanced and intermediate stuff. So that's coming later. But once we get around like that March level, that's when I want to start kind of pulling in students and alumni and community members and such of like, and even like CDA alumni that graduated from like 3 years ago. You know, like I'm going to be kind of reaching out to everyone and doing little fireside chats and stuff. So that being said, okay. Good start to the day. Great news from Ariel, and let's get to work. Let's get to work. We got work to do. Doesn't matter if you're tired. We got stuff to do. Let's do this. Also, so I'm also really excited too because I got a stream deck. I put inside Discord. I was pretty excited about that. Like now I can like press a button and I can turn things off and on like on stream and stuff. It's so nice. Like I can go back and forth through the scenes. I don't have to kind of like tilt my head back in as much, kind of looking at things, making sure things are working properly. That's really handy. So that's gonna be exciting. Hopefully I won't mess up the iPad this time as well. So I can be able to kind of go off and on. And I'm going to be messing around with some different views as well. So check this out. If I do... No, I don't have it like set up yet. But what I want to be able to do is... bear with me. This is going to like kind of zoom... The stream itself, I kind of like go, it's like back and forth, back. So, yeah, the audio isn't set up properly on the other one yet. Yeah. So it definitely cut me off there a little bit. Yeah, but I want to be able to like go back and forth, and have different views for different things. Like let's go into like drawing view mode and zoom into something so that we're not just always like stuck on a static view and I have to like slide things in and out. But I can actually do that now. So I'm pretty excited about that. And yeah. So a little stream upgrade coming as well too. Cool. Okay, well, on that note, let me actually get the iPad set up properly. See, there you go. I can kind of like pop that on and off screen now. Super nice. Okay, let's connect though. Nice. Okay, there we go. Cool. Yeah, it's really handy, Doug. Like, I recommend like anyone who wants to get more into actually like streaming views and things, and even like teaching in class. This is going to be super handy for the CDA cohort that we're going to have. Just being able to like put things up on screen and stuff and off as we go. Okay. So where were we? We last left off. I wanted to add a little note over here. So we actually added the first resume bullet that's been unlocked now for the GRC portion, added in the last night. But again, every single module will have like a resume bullet unlocked as we go. And all what this really means, just like a little reminder, is you can take this and you can kind of wordsmith it around and adjust it as you need. It's a starting point as a, excuse me, as a bullet point for you to put on your resume. And you don't have to put all of the resume bullets on your resume per module because that's too much. But the ones that you want, here's some like starting wording that we think sort of explains and covers what you're able to do. So like for the GRC side, once you go through the module and you feel somewhat confident about it, then you should be able to say that you're at least skilled in implementing GRC frameworks by conducting a cyber risk assessment, which you've been able to do inside of the lab itself with the Good Corp notes. And you've also been able to implement best practices using something like the CIS benchmarks. So again, just that's up, but a reminder that you don't need to put your resume full of bullet points and full of skills because that's too much, right? So pick and choose the ones that you think are good. The SOC100 covers a lot of ground, and then you can, of course, adjust the wording as you see fit. These are just sort of like starting points for you to work with. Cool? Yeah? Sounds good? Beaver logic, hoard them like a dragon. Absolutely. Got to catch them all or hoard it like gold, like smog. So, cool. Let's go. Cryptography now. So, where are we at over here? We last left off at like the general concepts of hashing, encoding, symmetric encryption. I think that's where we last left off, yeah? So we're going to go into a bit of lecture mode and talk about a bunch of stuff. And then we're going to do a recap of things. So, let's go. So encoding, let's start off with encoding because we didn't touch that point of that last time. All right. So encoding is essentially just, it's more so concerned about converting data from one format to another. That's the way to think about what encoding is really designed for. Coding is not encryption. Encoding is not encryption. It's not meant to obfuscate. It's not meant to provide confidentiality. It is much more about providing integrity. So that's how you need to think about what encoding is really for. It's not a security mechanism, but it's part of the components that make up the general process of encryption and decryption. Because at some point, you're going to have a mechanism to encode things. And this is all about integrity. And remember, integrity, right, is about trust. It means that you can trust the data. So we have this for the reason of, have any of you ever played, like Broken Telephone back in school? Or like Purple Monkey Dishwasher kind of thing? You ever heard of like one of those? One of them should maybe trigger. Really? Yeah, Bearded did. You didn't play Broken Telephone? KS didn't? Yeah, okay. Karina did. Yep, Doug did. Telephone. Telephone. Okay, so Broken Telephone. It's a game played in a lot of like elementary schools when you're a kid where, and it might have had a different name depending on like what school and where you're from, etc. So the concept is that imagine you have like a room of people that are trying to pass a message back and forth. Okay. And it's actually like a bit of a thought experiment as well too. Ariel, yeah, when you tell people a message, and I mean even beyond this game of Broken Telephone, but what it's supposed to try to explain to you is like you start off with one person and you start off with like a simple message of like, hello, my name is so and so. And then you get like 30 kids around the room, and the first kid says the message, and they just keep saying to the next person, okay, so I said this, now say this to the next person. And they just keep passing the message back and forth. Now, like the vast majority of the time, by the time the message goes all around the room, it's almost completely changed. There's things added on, there's things lost, there's some slang, there's words and letters dropped. Things always change. And, you know, think about maybe like all of us see headlines on the news. People have a habit nowadays to just read a headline and pass the message. But they don't read the article. And you don't know where the article came from. And you don't know what that person wrote to get the article. And you don't know where that person who even provided the data for the person to write the article even got their data from, and so forth. And another example would be like everything that I just said. Are any of you able to like fully recall it? Like word for word, verbatim? I highly doubt it. You're understanding, you're paraphrasing, you're sort of internalizing stuff. And encoding is meant to prevent any loss along those types of processes where data is exchanged from one person or one thing to another. And what you do is, instead of trying to pass a long message or different language where maybe people speak a different dialect or they have different slang or different preferences in how they say things, encoding is meant to sort of translate and transfer a generalized or I shouldn't say generalized, but it's meant to translate or transfer data, words, language, etc. into a standardized language. I guess you can call it that to some degree. Now, it's not a language where you could use to speak, but it is a language. And it's meant to simplify things. It's meant to standardize things and remove the ability where messages could get lost. That's really what it's about. So Kim's saying encoding is more of standardized formatting like ASCII or Morse code. Effectively, yes. Bearded says, sounds like next year high school is changing what I said. Yeah. Yeah, I guess we've all had a partner or something at some point, right? Like, that's just how life goes. Ariel used to call it Chinese telephone. Really? I've actually never heard of it called that before. I don't even know. Like, that's an interesting one. All right, and then KS, you've had Messenger. Yeah, so Messenger is another way of calling it too. Doug, thanks. So that's really. That's an important part to really understand here, because a lot of times when students first start, they're like, oh, like here's base64 encoding, or here's like URL encoding. Unless you really stop and take some time to understand it this way at first, there's a bit of a fallacy where a lot of students hear and imagine encoding, they start to think that it's actually a form of encryption or a form of providing security or obfuscation, and it's not. It is not that at all. So, integrity. It's integrity. It ensures that you can trust and you can translate and transfer very complex, unsupported or loosely supported, I should say, even data into a format that is easily passed and exchanged from one endpoint to another. So if I'm going to be kind of drawing this over here now, like imagine I had computer 1 and I want to send something over here to computer 2. Now, let's just say I'm trying to send like a weird encrypted kind of message over here. Okay, so imagine I've encrypted something so you can't read it. And I want to send that over the wire to computer 2. Well, there's some problems over here. There's some problem characters. Okay, like things like backslash, I should say, let's just do 1. Backslash, / colon, semicolon. These things are actually already stored characters that are meant to do certain things in computer languages or computer code already. Backslashes can represent like an escape character. And you know, / can denote directories, paths, right? Colons can represent like key value, and I should actually be writing these things down. So like this would be like escape characters. And escape characters mean like tell the computer to ignore it. / could be like paths. Colons should be Spence, thanks for the follow. So colons could be something like key value pair. Kind of like the registry, like we talked about, like the registry in the past already. Semicolons could denote like the end of, or like end of code. Now, these are perfectly normal characters that we might use in like the English language when we're trying to explain something or reference something. So what happens is if you try to send these types of characters over the wire, things could break because the network protocols, like, it's an unrealistic expectation to assume that every single network protocol and every software and every version and every port, etc., should support every type of character and every type of possible combination. It doesn't make sense. So what we've done with encoding is instead say, okay, instead, before we even transmit or transfer characters and data from one endpoint to another, let's just wrap them up into this encoded language. And this is where you get something like maybe like Base64. And what I can do over here is say something like Base64 encoder, just for the hell of it. We're gonna use CyberChef later, but like, hello, my name is Anthony. So if I did something like this, right, and I hit encode, you can see it sends like this weird string of characters. But it's a finite amount of characters. Cool. I got a new sub goal. Well, thank you to whoever just subbed. All right. So it's not telling me who subbed. That really kind of threw me off for a moment. I don't know what just happened there. So imagine I had something like that's what it was. Okay, so KS, you resubbed. There was a bit of lag. Thanks for the support, man. Don't apologize, but thank you for the support. Seriously, it's helpful and handy. Cool. So, Windows System 32, right? If I went to this directory, well, I could go and I can encode this because there are some characters inside here that could entirely break something, right? Like the backslash, the colon. If I were to encode this now and pass that message along, I can translate it to a Base64 encoded version, which has characters that are effectively reliably supported through any protocol, port, service, URL. It doesn't matter. Like you could take this anywhere and I could pass this message to anyone. Like I could put this inside of chat. And if I were to say, hey, go ahead and Base64 decode this, well, let's go and do decode now at the top. So if I go and I decode that now, it's always going to be the same result on the other end. That's the point of encoding. That's the full intention. And this is important to really hit home because you're going to see encoding everywhere. Everywhere, everywhere, everywhere. Spencer's saying it's also good for binary data for which there are no ASCII characters. Yes, exactly. So when you're dealing with, and we're going to show that later, when we actually encrypt and we lose the support of ASCII characters, or when we're dealing with simple binary files, whole bunch of zeros and ones, etc., and other like weird characters that gets created and compiled, you're going to see it's everywhere. So we're going to get to that later, but when we do the lab, you'll actually be able to see it in action. So pretty important concept to hit home. Now, if you really want to sort of summarize it, I'm gonna give you one word that I think really does a good job of summarizing it, and it's actually about. Put the old iPad up. Compatibility. That is what it's for. Compatibility. So far, the encoding has been designed for data transfer, data persistence. Do we define there to be things like error correction too? I mean, it's part of it. That's what compatibility will be able to provide. It's to prevent things like errors, and kind of going back to above. It's meant to ensure integrity, which means you can trust the data. And it does this by providing compatibility between dissimilar data exchanges, endpoints, services, etc. So, important. Now let's talk a little bit next about hashing. Okay. So you're going to hear, and I think a lot of students always hear like the textbook answer at first, like, oh, this is it transforms like any input into this fixed length string. And that's it. Like, yes, that's what it is. Or you might hear it as called like a one-way function. There's a couple different ways to think about it. And then I'll tell you how I think about it. And this is also for integrity as well. It means that you can trust. Karina is saying there was coding is a language question further above a cast. Not sure if we had a chance to answer it. No, I didn't see that. What was the question? Coding is a language. Is it fair to think about it like translating maybe? I think, yeah. I think I did say that at one point. That, yeah, encoding is sort of like translating. Yeah. Thanks, Karina. Think of it like translating as well, yes. Okay. Now, what I like to think about, like with hashing, that really, it kind of stuck with my head, was it is yes, it is a one-way function. It is a one-way process. So, what is another one-way process? Well, let's say we took an egg, right? And we cracked it. Now, you're not going to be able to put that egg back together. Flex seal. Oh, man. Okay, maybe with Flex Seal you can put it back together. Now, this is a one-way function in real life. You crack an egg, you make an omelet, right? Now, the result of the cracked egg is still the egg. Like, you still know it's the egg, right? Like, it's just cracked. It's no longer the same, but it's now represented by this cracked pattern. And you could break that up even further and say, okay, well, let's say that the egg kind of broke in a certain way, right? Something like this. Now, if you wanted to, you could sort of put the pieces back together, and you could do this with a mirror as well, too. Doesn't matter. Just think about like cracking something, but they're both sort of the same. Now, you could reconstruct the egg and put some Flex Seal on it, and sort of glue it back together with the cracked shells, and you would still know that it is the egg. Like, it's just the egg that's been cracked into different pieces as a representation. Now, it's easier for a computer to recognize and provide a sense of integrity by kind of looking at the various pieces of an egg. Like, you crack an egg into it's all shell pieces. The computer can put that back together very quickly. And you could too, if you really like spent time in it. Like, you could. It's just going to be like really, it's never going to be the egg again, right? But the semblance is there. And that's how a computer sort of works with a hashing function, is you take something and you run it through a process whereby you can't fully reconstruct it back to what it was originally, but you get a representation. Your output is finally a representation of what the data or what the thing was. And that's how you create a hash mathematically. It's the same concept. And now what I can do is I could say, okay, this egg over here at the top, if I break it a certain way with a hash, like a hashing function, all I really need is like, just give me like this piece over here. Okay? That's the hash output. That's all I need. Because if I look at that, then I know that that was enough to tell me that came from this egg. Like, I know that this egg has this cracked piece over here. And that's how you can verify that's where it came from. Now, another egg won't be able to do that because another egg, another piece of data might be a smaller egg. Or you might have a kind of like a more oval, kind of like lopsided egg. And now you can't actually... Okay. So if I were to try to take this piece of the egg, right, and bring it over here, well, it doesn't fit there. So I know that it didn't come from that egg. If I try to put it over here, I know that it doesn't come from that egg as well. What I can say is that every time I crack the egg through this process, this function, I know that it could always be coming from this egg up over here. Therefore, I can trust that the top that this egg at the top is the one that's always going to be the egg that piece came from. And what we're looking for here, this is the hash. This is what the hash actually is. It is a small piece. It's a representation of something much greater and much larger. You could get like a 5 GB file that is massive and enormous, and you could run it through a hash function, which gives you a very small representation of what it is. And you can trust the function that it's always going to be, that 5 GB file of data is always going to be broken down that certain way. And this is where the mathematics come behind it. Because if I were to grab the egg and if I were to drop it on the ground, it's entirely random. It's effectively always going to look a little different. A hash function says, well, we're actually going to get that egg and we're going to drop it at this speed, at this height, on that surface every single time. So therefore, that specific egg will always crack and always look that exact same way in its broken pieces every single time. And this, as you can see, starts to create an observation of why some hashing functions can become vulnerable. And this is why we have very advanced hashing functions now. Because if I had a weak hashing function that I could always guess that the egg perhaps would break a certain way, I could expect and sort of assume piece by piece that if this egg is broken that way and it always looks like this, well then another egg broken that way will always look a similar way too. And then I can start to piece it together and figure out similar patterns. And that's how you can crack. That's how you get bad hashing functions. Now, there's some properties that we're looking for to ensure that this can't happen. So we want a strong hash. Or I should say, a hard to guess way of breaking an egg. And what this looks like is small change in data equals huge change in output. So censoring, you only really need to know that you crack and compare the piece. Yeah. You can hash a whole book, kiss, saying, and hash digest will still be the same length as a sentence, of course, and it will be unique. Yes. Exactly. Like, you can take a whole textbook and... You know what? That's actually, that's another good way to think about it too, is the title of the book. The title of the book and the author is going to be the same. Okay? Like, if I were to say, like, if I'm trying to give you a message across, I'm not going to give you every single page to verify that this is the book. Instead, I'll be like, okay, here's the author, here's the title, it was made on this date, and it looks like this, like here's the cover, etc. I can give you a very small representation of what the book is. And you can know, okay, well, if that's the case, then it is therefore the same book that they're trying to tell me without having to physically give me the book. It's an integrity, it's a verification check, and you do that in a very small representative way of the larger sum of what the thing actually is. So that's another way to think about it. The title of the book, or a piece of the cracked egg that will always break the same way. Does that make sense? I'll pause there. Because I really don't want you to be thinking, oh, like hash is a one-way function. Sure, it is. But if you actually understand maybe some other real-life examples of what that looks like, then you can immediately understand why some hashing functions are therefore just vulnerable. Like, it should click right away, right? And I'm seeing some yeses in chat, so I'm going to go with a yes. Spencer, you think egg is a bad example since real life you can't re-break it? Well, that's the thing. Like, you're not supposed to re-break it. You're not supposed to try and put it back together. It's a one-way function. So therefore, I think it's actually a pretty decent example. Because if you get an egg and you crack it, it's going to break a certain way. But you shouldn't be able to put it back together. Now, what you can do is look at a piece of the shell and say, okay, well, it came from that egg. And a hashing function is going to say, well, in fact, we know that every time you take that exact same egg, like if you're able to sort of reproduce it or remake it, it's always going to come out that same way. Chrome. Yeah, I was just giving an example right there. Welcome back to the chat, Chrome. Creating a hash is the book contents, like file contents, and not including the book title, file name. Though, is that correct? Spencer saying, in real life, you can't verify the egg hash by re-breaking the original. Okay, yeah, so I see where you're coming from. I think, so try to think of it like this. Imagine you have the egg that is, you can reproduce this egg. It's always going to be the same. So in terms of the one-way function concept of what we're trying to get across here is you break it, it happens once, you can't put it back together. Like you cannot reassemble the broken piece, and you cannot take the hash and reassemble the thing. That's what I'm trying to get across, where when you actually drop or crack that egg, you cannot reassemble the egg anymore. But imagine for a moment that you were able to reproduce that same egg over and over and over and over again. And that's the data. That part is always going to be the same. But once it goes through a process, you can never put it back to its original state. Now, when we're talking about a good hashing function, I think that's kind of where you're going from, is a good hashing function, and that's what I said a little bit before, is this is where the math comes in and kind of takes that analogy one step further and says, okay, now let's continue with this this is a thought experiment. If we were now to calculate that we could break that egg exactly the same way every single time, same height, same surface, same weight, etc. every single time. Therefore, the crack pattern will always be the same if you take that specific egg. Now, if you get a different egg, you get a small egg, the crack pattern will be entirely different. And that's the concept of what hashing is trying to provide. It's an integrity and a verification check that if you take a certain input, you put it through something, and then it turns a certain way, the output is never going to be able to be reproducible. So it's more like a rock, as if you break it, you'll have... Well, that's what I said, RTSR. Rock, mirror, egg. Think about breaking anything as like a one-way function, and that you cannot reassemble back to what it was. The output of that is going to be your hash. And all you need, perhaps, is a piece of that output to verify where it came from. And that's all what the hash is trying to provide. Verification of where it actually came from. And we can assume, mathematically speaking, that the hash function should therefore break whatever it is. The rock, the mirror, the egg, the box. You can give any concept there. For me, it sticks with eggs. I love eggs. Now, the mathematical function should say, if that thing is a certain size or representation every single time, it will therefore break the same way every single time. That is a good, reliable hashing function. That's what hashing actually is. So, but if you understand that process, then therefore you should immediately understand where vulnerabilities can occur as well too. Because if I were to get different shaped objects and break them through this hashing function, and I started to notice a pattern between how they broke, then I can start to put back together some level of maybe like resemblance. Like, okay, if it breaks this certain way, well, then I can always expect this pattern to appear. And then what hackers do is they look at patterns and then they start to associate things. And they say, okay, well, if I have this pattern, this equals L. If I have this pattern, okay, well, this equals A. That's where the problems start to occur when you have a weak hashing function. And therefore, if I were to say that we have maybe like one egg here and a bigger egg there, and the hash out of this is maybe like LA, and then let's just say I change this a little bit, and the output of that was LB, well, there you go. This is a bit of a problem. We should expect a good hashing function to say it should be something like drastic, like absolutely drastic. It shouldn't be that close. It shouldn't be like LA to LB. A good hashing function should say something instead. So this is bad. And a good hashing function instead would be something like LW, right? Like something really far from it. That's a good way to break it down. Okay. So Baloo, you're making hash and eggs after this? Yeah. Damn right. Damn right you are. You will not be able to rebuild them together to get the first one. It's right, RTS, yeah. So Spencer liked the example of a book. The hash could be the first page written in reverse. Obviously not a strong hash function, but it helps understand you can't reverse it to get to the original book. Well, I think in that example you could. I think you could actually, you could reverse the page quite easily that way. So I don't know if that, I mean, if that works for you, great. But I think that if you kind of go in with that understanding, that might come back to kind of hurt you a little bit as like an understanding of the mechanism for it to be that easily reversed. So MPOP saying, so with encryption, you can decrypt. With encoding, you can decode. But with hashing, exactly. So you can't reverse the hash. Perfect, MPOP. You can only get the same hash output by using the exact hash input. Correct. Yes. So if your input is always the same, your output should always be the same as well too through a hash function. But it should be representative of the input, and it shouldn't be anything close to the ability to put it back to what it actually was. Lieutenant Dan saying, is that like frequency analysis? Yes. Yes, pretty much. Kim Fried saying, so programs like Hashcat are used to try the hashes from rainbow tables and not the actual password. Never had brute force password, but I guess that'll be part of a lab. I think, I don't know if we're going to do any brute forcing in this course. It's a little bit out of scope for what you need to do, but maybe we can do stream on that later. Spencer, you could reverse the first page back, but you don't have the rest of the book. Well, that's sort of the problem with your example. That's what I'm trying to say is you should be able to have the entire book. If you're only giving me the first page and giving me a hash, then that's not the same concept. You should be able to take the entire book and run it through the hash. And if you were to then say that your hash is the result of reversing the entire book, that's not the point. Because that's too big. That's not a hash anymore. That's actually encoding and decoding. Well, that again, Spencer, that's not going to be the same thing. Because if you're just, then how do I know that the rest of the pages are from that book as well if you're only giving me a one-way function of the first page? The one-way function has to be of the entire thing. Well, again, then it's not a hash. So it can't just be the first page. The hash has to be the entire book. It can't just be the first page because then you can't trust the rest of the data and therefore it's not actually a hash function. What you're saying is you're actually saying that that's like a... that's an excerpt. You're saying that like the example you're providing provides an excerpt of the data or a foreword or like a pre-word or pretext or preamble. Those are different functions. That could be a preamble. It could be a sequence number, like we're going to start at this page, but it's not a hash. Doug saying Anthony's hitting on what I discussed yesterday with secure hash algorithm, going into details. Yeah, exactly. Yeah. It's important to understand these differences because they do matter. It's actually quite important because if you are off a little bit, then this might come back to hurt you a little bit in some ways, like when you're trying to compare hash functions or you're trying to look at like hash vulnerabilities of why they actually even occur in the first place or how they can be abused or misused. Advanced stuff, mind you, but it's important to get the foundations really nailed down. Cool. Nice. Okay. We're going to take a little bit of a break here as well, too. Yep. That's all good, Spencer, yeah. Wild piece is like when you put into a blender ingredients to get a smoothie hash after blending. Exactly, yeah. You need the entirety of the data and not just a representation of it to put through the hash function to get the output of a true representation of what it is that can't be put back together, but should always be broken down that exact same way. Anything less than that, then you're not actually providing a full representation of what the entire data actually is, and that's how you actually get vulnerabilities. A bad hashing function would take the first page, like kind of what Spencer's saying, or like one ingredient. Like if you're cooking, so Doug's saying, or Wild Piece is saying when you put a blender ingredients to a smoothie, imagine you're trying to make a smoothie and you blend it together, but you only put in the first ingredient out of 6. It's not going to be the same. The output is not the same. Like you can't trust it. But if you put in all 6 ingredients and then you blended it and then you got an output, same thing. That output is the hash. Like if you took a sip of the smoothie, you're like, okay, yeah, that tastes like it every single time. Perfect. That's how you need to think about it. You crack an egg, awesome. Perfect as well too. So interesting, but hashing functions can also be used in programming or databases. It doesn't necessarily have to be good for cryptography, and sometimes it's good to have collisions. Well, we're talking about cryptography. That's what we're trying to talk about here. We're trying to talk about like the hash of data and trying to get the full output. Sometimes it's good to have collisions. Tell me when it would be good to have collisions. Then we're going to take a break as well too. Just waiting for Spencer. I would like to know when collisions are good to have in hashing. And if we're talking about programming, like if we're talking about speed and effectiveness, or maybe like algorithms to like speed up search functions, maybe. But I think arguably that's an entirely different discussion on features. Well, exactly. That's what I'm trying to say, right? Like we're talking about cryptography. We're talking about like verification of entire data. That's what we're trying to provide here. And a hash is representative of the entire data. Now, if you're talking about having collisions intentionally for like a programming perspective to be able to get a fast lookup of like a snippet of the data and then look and trying to get a collision, then fine. But that's an entirely different discussion. That's not actually what we're talking about right now. We're talking about the fact of we're trying to get like a 5 gigabyte data, and we want to verify that that 5 gigabyte data is the same 5 gigabytes, the same structure every single time. That is what we're trying to say in terms of a hash. So hash function is like a coffee machine. The same ingredients and the same setting should always output the same coffee, but you can't get the beans back. Exactly. So everyone, I think everyone's really getting the point home. What we're trying to discuss here is a hash is. I think everyone's got it. Spencer, I think you're going off on a bit of a different way of trying to look at it. I understand your use case and your purpose, but I think that's a little bit misrepresentative of what we're trying to communicate here as well at the same time to the students and the audience. If we're talking about a hash function for a full verification check of data, that's what we're looking for. We're not looking for programmatic effectiveness or optimizations or tuning where we would maybe want a bad hashing function with collisions for a quick check to go over a database to speed up the database check so that it's good enough. Because that's not actually, that doesn't provide integrity. And we're trying to look at this under the lens of we want to hash something with full integrity, and that's what we want to be able to understand of a good hash function for our studies. And a true hash function is meant to provide you a one-way function. Now, if we want to trade off between speed and accuracy, all what you're actually doing there is using a bad hash function that is not well designed, that doesn't actually provide integrity, and therefore doesn't actually provide the hash function that we're trying to provide over here. So it's sort of like, it's like if you were to take a blender and you throw all the ingredients in, and you get a drink, and you can trust that drink every single time, then great. Now, if you wanted to maybe, and say you needed to blend it for 1 minute, then like that's your recipe. That's your verification check. That's a good hash function. Now, if I were to take maybe 5 out of 6 ingredients and then I provide it to someone and I said, well, hey, yeah, that's good enough, then that's more what you're trying to describe, and that's not actually what we're trying to provide here as a verification check. Again, that's like a snippet of the data. R double saying, I'm confused on how it creates a function, but that's not considered encryption. Is it because it's one way? So it's not encryption because it can't be decrypted. That's why. Encryption means that it can be decrypted. Hashing cannot be decrypted. Correct, yeah. So okay, saying, so for encryption, you need a cipher to encrypt and a key to decrypt, correct? Yeah. Well, I should say symmetric encryption. You need a single key. We're going to talk about symmetric and asymmetric as well, too. Okay, let's take a break. Break. One last question for our double. But can you check the hash on the other end to verify integrity? Correct. Yes, it should be the same hash every single time. And if it doesn't do that, then it's a bad hashing function and it doesn't actually provide a reliable means of integrity for performing like cybersecurity triage and integrity and trust verification checks. Yeah, exactly. Nice. Okay, good. I think everyone's getting it. Yeah, you grab the file and hash it, and if the hash matches the original hash, then it means you have the same file. Good. Good. Perfect. That's exactly what we're trying to be able to determine over here. So like if all we cared about was like, take a look at my drawing here, for example, and to sort of like delineate this a little bit further, is if all we cared about on our hash output was to determine that it should be L, that's sort of like what Spencer was trying to say, was like you could run any hash function that is just reliably providing you L to ensure that your data is good enough, and from like a programmatic perspective, but that doesn't actually provide you full integrity because you could be missing out. There could be, like, you see how I have A, B, and W? If all I cared about was the L, but then I had different data beyond A, B, and W, well, then I have a problem if I'm trying to perform cybersecurity triage. If I have like a memory forensics file or a captured disk file that I need to go and perform forensics on, I want to be damn sure that the rest of that disk is 100% was representative of what happened on the incident. I don't want to run a bad hashing function that provides me a snippet of, okay, well, it's an L, it's good enough, I can work with it. Because if the rest of the disk is not representative of it, then I can't perform forensics and then I fail my investigation. And I could make some really bad results for it. Now, if I am just doing like a check and balance, and this is kind of like, imagine you were to go to a winery and like tap a keg. Like imagine you have a winery of like 100 casks and you go and you check like a sample of each of them. Okay. Like you take like a shot of each of the kegs, and you're probably really drunk after, but you do that and you're like, okay, I'm going to give this like 100 because they all taste kind of good. But then when you sell the wine, and then 5 customers come back, out of like 5 of the kegs come back that weren't good, that is indicative. Then that means like your process to get a sample of what it actually was, like representative, is not good. That is how you could have like a bad hashing function. However, if you are only caring about like 95% accuracy and you don't mind having some inaccuracies from like a programmatic perspective, then fine. Like you could do that, but you have to go under it in the context that it's not fully representative of the entire picture and you're making assumptions, and therefore you don't have integrity. Does that all make sense? Because I really need to grab a cup of coffee over here. And then we'll take a break. I really want to hit that point home. Nice. Okay, good, 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 good. Cool. Womps, T-Long, Gemini. Thanks for the follows. Gemini, how long have I been live? I don't know how long I've been alive. That's another question. Are any of us really live? No. We started at 10 a.m. It's like an hour ago. Hash the beans and then digest. All right. Break time, break time. All right. Okay, let's get back into it. Okay. So let's take a look at the chat over there. So DF is somewhat different than IR, even though they are part of the same acronym. DFIR, yeah. Doug, yes, sorta. So DFIR is, yeah, it's incident response. You do incident response and DFIR, but that is not all you do. DFIR is forensic side of cybersecurity, where you're looking at the pieces and evidence. In digital forensics, you can handle data, so it keeps highest level integrity, so it can be used in legal matters and everything to help you restore operations back to normal. Yeah, good answers over there. Yeah, so another good way to kind of think about it too is that like digital forensics is trying to work with the highest level of integrity as possible, assuming the goal should be 100% integrity for a full representation of the chain of custody of what actually happened. Like, what are the events? It's kind of like a law case. Imagine you went to court. Well, the court wants to know exactly what happened. Like we need to know the full evidence that happened from the beginning to the end of whatever brought them to court for an investigation and a ruling to be made. You can't assume, and you can't just say some evidence was left out and then say, well, we're going to make an assumption that we're like 95% accurate. No, well, the court's not going to work with that, right? That's where cases get thrown out because you can't trust it. So that's like digital forensics is trying to work to the goal of 100% accountability and recreation of the events that happened through like memory forensics, disk forensics, text, email, documentation, etc. Like a chain of events that happen, events and logs. Now, incident response is about putting out the fire. So incident response is not necessarily so much contained about, and that's kind of what like KS is saying there towards the end, it's about trying to restore business operations back to operating capacity. Incident response might mean that you have like a compromised endpoint, you triage as much as you could, and if you're not confident that you're able to remove or quarantine whatever is happening to it, well then you might need to like reimage it to a known good trusted state with 100% integrity. And that's where a hash check would come into function. You would have a hash of like your known good trusted Windows endpoint, and it is representative of the entire Windows endpoint. The operating system, the files, the disk, the memory, everything. It's the whole book. Like the whole thing needs to be accounted for. And then you get a hash output of that, which is like a snippet, like a statement of what it is. And then you refer to that hash, say, okay, I trust it. That means the entire thing is good. I can now restore the image because I can't be confident that I've been able to remove everything here. That is an example where you don't want collisions. If you had a collision in that case, that's a problem. If you had a hash that didn't provide full integrity, then how can you trust that the workstation's free of anything that could compromise it? So this is why it's so crucial. And now incident response, like I said, is about putting out the fire, but it's not necessarily about getting to the root cause. And that's where the DF, like the digital forensic side, comes into play. So incident response has like playbooks and things that like imagine you had a fire at work, right? Or like an emergency at work. There's a process and things you follow, and that's effectively like your playbook. Yeah. Yeah, thanks guys. Good explanations above as well too that I'm just kind of riffing off. So precision matters. You have to be very precise with this. This is why also, this is why you can have like just digital forensics specialists. Now they also go hand in hand, because if you're a small organization and you work as like a SOC tier 2 analyst and up, part of your incident response is also going to be collecting chain of custody of evidence and forensics. So like you'll have a process to snapshot the endpoint and quarantine it, etc., and also respond to putting out the fire, and then investigation later. So forensics is post-incident, and some of the collection happens during the crime. Like, you know, like imagine, like you've all seen like CSI, right? Dexter, like those shows, right? Like they show up to the crime scene. Well, The cops responded to the crime, right? Like that's the incident response. But then part of the collection afterwards is like, okay, well, like what happened during the crime as well. And then that's the digital forensics portion. And that's why I said my advice is when it comes to cybersecurity terms and definitions, when in doubt, always try to think back to like real life things and like what is the English meaning of the word. And I think that can also help kind of guide when you're in doubt. But cool. All right. Good stuff. This is where it starts to get more exciting. So I think, what's the next section over here? We covered hashing, we covered encoding. I think we actually, yeah, we wanted to go and move to sort of like a breakdown. We wanted to actually walk through the TCP. So we covered the TCP handshake already. But what we want to do now is kind of cover the process. Like, how does this actually all work? How does this all happen in tandem? With like symmetric and asymmetric encryption, which we covered last week to some degree. So how does your computer connect to a website and trust the connection, right? So up to date, we've looked at the TCP connection. We've looked at the TLS, the three-way handshake. We've looked at the sequence, right, of how it's established, SYNS and ACK. We looked at the TCP flags. Excuse me. We looked at the sequence number, the acknowledgement number. We've looked at how this is all set up. And we had a brief introduction to like the client hello, the server hello, right? So what we're trying to establish now is how does this really all work in tandem? So let's kind of like walk through that together. Cool. Alrighty. Make sure I can see my screen, yeah? So my iPad's up. Yep, it's up. Good, good, good. Cool. Alright. So, step one, right? Step one is we have our SYN, like our initial TCP packet. So we have a TCP, and I should say, you know what I'll do on the side actually? Is I will say client to server. And I'm going to represent this just so I don't have to keep typing or writing that, rather. I should say C2S. Okay, just so that we're all clear. Yeah, we got Demori back in chat, CI. All right. Okay. So that's the first part. And remember, during this part, we have our initial sequence number that's sort of thrown out. And just for simplifying things, right? Cyber Saiyan, nice. Subscribe to the Prime. Thank you. Thanks for the support. Thanks for being here as well, too. So sequence. And let's just say, I don't know, like for the sake of it, because we're not looking at a PCAP, we're just going to make some general assumptions over here. Let's just say we want to start with like the number 100, okay? And this is effectively like just imagine we have the client saying like, hey, imagine they're like shouting from across the room, right, to one another. And the client's like, hey, I'm going to start a conversation with you in like this crowded room. And to make sure we don't lose track of things, I'm going to start with 100. And that's effectively what this like the SYN process is. And we touch base on it in a bit of a technical manner back in the TCP handshake, but we're going to generalize it a little bit more so we can kind of move along, because we don't need to go step by step through the PCAP headers and frames. So let's just say like Alice, right? Because we're in cryptography land. Alice is trying to talk to Bob. And there's a whole room of people on the internet right now, right? So Alice says, let's start at 100. Okay, so this is like the SYN flag that has been initiated right now. So then we go to the next step. So step 2, we now have the server going back to the client. And so this is Bob responding back. And we have the SYN ACK. So the SYN ACK flags are set, right? So there's something like, remember, it's kind of like this. It's kind of like a 1 and a 1 set over there. So we're having those TCP flags set over the stream to indicate that now Bob is responding back to Alice. So like, cool. All right, let's have a conversation then. You're starting at 100. Well, I'm going to start at 400. And again, these are just generated numbers. They, as we saw, right? These could be large numbers, small numbers, and then there's a length. Bob and Alice from Sands. Yeah, I mean, we're back in cryptography, right, Doug? So like, we got to stick to the industry. So let's just say like an ACK of like 400. So Bob's saying, okay, I'm starting at 400, and you started at 100. So I'm expecting you now to continue at 100. And you, Alice, should respond with 101. Because let's just say we're going to count up by 1. We're going to excuse the length size for now. We're going to go back with that incremental counter that we saw inside of the exchange. So that's all what's effectively happening, right? From like steps 1 to 3. So Alice is now responding back. This is the client server. And responding back with their ACK. So yeah, weird. Okay. Look, the screen didn't look like it was refreshing for a moment. Okay. So now we have this exchange. Alice is now going to be responding back of this number. It's always going to be like it's incremental, like 101, 401, 102, 402. And we just keep on like incrementing this counter, right? And now from then on, it's just going to be, and this is how you create an ordered exchange. This is what the three-way handshake is, as we talked about before, is to create reliability. It's to create essentially a form of integrity, a form of trust, that we can always assume that if it's 100 and acknowledgement numbers, it should essentially always have like this sequence. Now, if these numbers are ever out of order, then we know that we have a problem. And that's all what the TCP handshake has done at this point in time. It just says, okay, from now on, Bob and Alice were across the room. There's a bunch of people in the middle of us. Whenever I'm saying, like, I'm going to be like, hello, 101. Bob responds back, hey there, 402. Like, it's just going to keep, like, going back that way, right? They're just going to keep on incrementing these numbers. And that's all those numbers are there, is to create an orderly value of reliability. So, what happens at this point is, how do we now, because we've established integrity, but how do we establish confidentiality? So now we move on to things, and we get into the TLS handshake, or etc. So we're going to say that So integrity has been established now. Trust. Now, yes, this is where, and some of you might be kind of reading this and you're like, okay, well, like, what if I hopped in the middle of that conversation? And this is how you get like those man in the middle attacks. So imagine for a moment, how would you stop that in real life, right? If Bob and Alice are having a conversation between one another in real life and there's a bunch of people in the middle of the room, what is stopping Jim? Let's just go with Jim. I don't know who a third person would be over here, but I feel like Jim from The Office would be like someone who's going to try to mess up something and play a prank, right? So imagine Jim comes in the middle of the conversation and Jim wants to interrupt the flow. So, you know, Bob and Alice have some degree of knowing that they're talking with one another because they've established this number, like 100, 400, 101, 402, etc. Jim could go in the middle and just start responding with 403, 404, like keep on jumping in the way and stopping Bob's transmission. But there's a lot of other controls in place that happen to make sure that that can't happen. To some degree, it can still be spoofed up until this point in time, but then you would have a breakdown in other network appliances and communication that we've talked about. Like something would probably be off with the router or the switch. It would look out of order at some point, like another device or something would have to be compromised to some degree. So we have this next step inside here to really make sure that we can trust this communication. And we get that by establishing confidentiality through means of encryption. So what happens now? Okay, so now we're back with the client, going back to the server. So we've established our order, 100, 101, 400, 401, etc. Now, the client is going to go back to the server. And we're at what, step 4, right? Yeah. So step 4. And now Alice does a couple things. Alice is going to send this message called the client hello. And we saw this inside the PCAP previously. And now inside of this package is going to include a couple things, important things. There's a lot of things inside there, but the important ones are the following. Client random. So this is a new random number. We're also going to say what code we can speak, like what encryption. So it's called supported cipher suites. And then also the version. So like TLS version. So there's 3 things here. And I'm actually going to highlight... yeah, let's use purple, I guess. I think what I am going to do is I'm going to erase that. And... just to make that stand out a little bit more. Because that's an important value that we're going to have. And this is sort of like saying, if we wanted like a visual, sort of like Alice is like, hey, I've generated like this random puzzle piece. And it's called like the client random. Okay. will do is... Okay. So these things are going to go inside this puzzle piece. And so Alice is sending this now over to Bob. We have a client random. We have a supported cipher suite. We have a TLS version. So we have a bunch of things inside of here that is effectively like Alice is saying, okay, like here's what I can offer. I'd like to establish a confidential chat with you because Jim is in the middle. Jim's like getting in the way. So Bob says, okay, let's see what I can do. So step 5, we now have the server responds back to, so Doug's saying, yeah, this also ties into securing data at 3 stages: data at rest, transit, and data integration use. Yeah. Okay. So a couple things happen there. Now, the server is going to also do something similar. Yeah, I wasn't sure where you were saying data integration from when they're talking, so I was like, what? Okay, data and use. That makes more sense, yeah. Okay. So step 5. So now Bob is going to provide the following. Bob is also going to provide a random number too, but he's going to provide the server random, send it back. And this is fine. Anyone can kind of capture this stuff at this point in time. It's not the biggest problem. Bob is going to provide a list of, like, it's not going to provide a list, but it's going to choose a cipher suite from what Alice has said that she can support. Like Alice says, I can speak AES. I can speak RSA. Like I can speak, and these are terms where we haven't covered like an extensive list, but consider these to be like languages. I can speak encryption language 1, encryption language 2, encryption language 3, etc. And a cipher suite includes a variety of things inside there. Yeah, AES, etc. So Bob is responding back with a new random value, server random. And let's just say that Bob chooses something like, I don't know, AES. Let's just go with AES 256, just for now, excusing all the other bits and pieces that could come with it. And Bob is now going to provide something called their digital certificate. And this is a bit of an important part over here. So, because this is how Bob is going to provide authenticity. We talked about that in the last stream. And this is kind of like that ID card, okay? So, certificate. So, all of these are now going into another puzzle piece. Okay. Now the certificate contains a couple things inside here. And this is kind of like I said, this is like, hey, this is my ID card. It is signed by a certificate authority. Thanks, Doug, with the explanations as they go. So a certificate authority, in this case, imagine like your driver's license that's signed by your state, your country, right? So it's saying, so whoever responds, it's a new piece. Yeah, so CI, like we're assembling puzzle pieces, we're going to put them together. And yeah, 256 bits of encryption. So 2 to the power of 256, which is an insane number of possible levels of encryption. So when we say signed by a certificate authority, we're effectively saying that like someone else that we trust has signed their certificate. And so the server, Bob, is like, hey, you can trust me because here's my ID and it is signed by the government and I have it and it looks like me. Like you see my face, I'm showing you, it looks like me, right? It's got additional features inside there, like the date of birth. date of process, date of enrollment, registration, etc. So there's a couple of things that are also provided with this. And it's important to note that we haven't really started to encrypt anything at this moment in time. Okay? So Bob is going to be providing some things to make this happen. So we have a public key. And what's happening here is a series of checks. So remember we talked last week, sort of like that chest with the two keys. Well, another way to think about this too, actually, I should say, is if you were to go to like a bank vault, or just think about like a box maybe. Okay. Yeah, cool. Still on screen. All right. Yeah. All right. So Bob is going to send over some information back to Alice. A server random, this chosen cipher suite, a certificate, including on these things is a public key. And that's an important piece to have. Because what's going to happen is Alice is going to use the public key for some level of encryption here in a moment. So I want to make sure everyone's following as well too. Does this make sense at this point in time? Okay, Doug's following. Is anyone still like a little unclear about like how and sort of the components? Okay, just want to make sure. I just want to give a moment because it gets a little confusing. It's a lot to sort of like mentally juggle at this point in time, right? Like this concept over here. Yeah. I hope that this illustration sort of helped a little bit more to think about like this lockbox, like the data goes in, the public key can encrypt it, and the private key can decrypt it. So this is why we're providing the public key to start this level of encryption happening. And I'll preface this. Encryption and like the general process of this kind of thing over here. Triple T saying, will you see both the 400 and the 101 in something like Wireshark? Yes. So I think, I'm not sure if you were on one of the streams earlier, Triple T, but when we covered the TCP handshake, we actually walked through the PCAP showing the sequence and acknowledgement number. So if you want to do the same, you can watch that video It's under networking, under three-way handshake. Or you could capture your home network traffic and connect to a website, and you'll see it there as well too. Okay. Yeah. Yeah, Doug's saying it's a lot and we do not know everything in advance. Well, yes, exactly, right? Like, this is why I am not going through the math over it, because, one, I don't fully know the math through it. I understand the concept of what the math is doing from an illustrative example as a concept, but I do not need to understand the math behind it. And that's what Doug and I talked about, like, yesterday's stream, too, is you could rabbit hole here really hard if you really want, and you can get really deep in the weeds, and that's fine. But if you're working in the SOC and you're trying to triage like email headers that are coming in from spoofed email that someone's just trying to put like a dropper or a rat on an endpoint for remote beaconing, that's more important to know. Like those triage skills, that's what we're trying to get you to understand that and work our way there. But we do not want to spend a large amount of time on this kind of thing. We're relying and trusting a professional in the cryptography field to come up with a good level of encryption for us to work with, that we can say, okay, we're gonna do this. So let's walk through like this box now, what's happening. So Alice is going to do this thing called a key exchange in return. So where are we? Step 5, we're over step 6 now. And this is the client to the server. So Alice is going to generate this thing called a pre-master secret. Because at this point in time, we theoretically should be able to calculate... let's not confuse that. We'll get to there in a moment. Okay, so Alice is going to generate what's called a pre-master secret. And now, yeah, we got a good size here today, CI. And then what's going to happen here is Alice is going to encrypt. Okay, she's going to encrypt now. Now, no one needs to have this pre-master secret other than the two of them at this point in time. So Alice is going to generate this pre-master secret. She's then going to encrypt it based off the information that she has at this point in time. So she has a couple things over here, right? Her client random, supported cipher suites. We have a public key that's been provided to us, and a server random as well too. So she's going to send this information and send this right now to Bob. That's effectively what is happening over there. And there's a term for this that you can look up for a little bit more. This is an actual exchange, okay? If I get this right. Is it 2 L's? I think it's 2 L's, right? Off the top of my head. Is it 2 L's or 1? I'm pretty sure it's 2. Diffie-Hellman exchange. Yeah, I'm pretty sure it's 2. And what this is effectively saying is Alice plus Bob can both can both generate this pre-master secret, I should say. And this is a key over here, without, okay? Without sending it in plain text. Because up until this point in time, anyone can capture this. Anyone that's listening on the wire can capture the client random, the server random, the cipher suite, etc. But Alice is now going to generate this information, which is called a pre-master secret. It's another piece of the puzzle. But she's going to encrypt it with Bob's public key. And then she's going to send it back to Bob. And this is why we have that illustration above. Pre-master secret Okay. So this is going to go through she's going to send this over to Bob. So this point in time, this is the Diffie-Hellman exchange happening in action. So happening in action. And what this is providing is something, it's another concept called perfect forward secrecy. You've heard this term before. Or if you haven't, you're going to hear of it now. But for those of you that I know are studying for like Security Plus and stuff, this is how we can conceptually explain what this is. We are establishing perfect forward secrecy, meaning that if anything is compromised along this process, so another way of thinking about it is from here on, we're secure. We just have to do the rest of the work now to establish things, but we have now established the start of where things begin in a secure manner, in a confidential manner. That is all what that concept really means over here. Because Bob and Alice now both have a couple of things. We're over on step 7 now. Okay, so now we're in step 7. And what we're saying here is Bob plus Alice now have the following. Because Bob was able to decrypt the pre-master secret. No one else has it. And this is where we now get the concept of perfect forward secrecy. So Bob and Alice now have the following. They have the pre-master secret. They have client random. It's 2. They have server random. It's 3. And what 3, so that's 3. And what they're going to do is they're going to blend this. Here's another blending that happens. Okay. A crypto milkshake. Yeah, milkshake. Yes, KS. So this is a KDF. Sorry, this is called a key derivation function. This is what this blend process is. And it's called a KDF. Key derivation function. Yeah. I know. This is why I said this is going to be, this one is harder to, like, as I'm explaining this to you, like, it's hard to grasp the first time. You're gonna go through it again. You're gonna go through it a couple more times, and it's gonna get a little bit easier. But it's gonna take you a couple times to really like, okay, like I can sort of do this. So my ask always that I tell students when we first go over encryption is, hear me go through it. We're gonna walk through it together. Take what you can. Take your notes. But if you really want to understand this stuff, you need to make your own notes. Like, this is one of the notes you need to make on your own. Don't just like look at mine or models or charts. This is one that you need to actually go and list out yourself and draw. Like, you do need a data visualization and some type of process flow to really make it stick. Optionally, you could generally ignore that and just generally understand this. Public key, private key means I lock with public key, I unlock with private key, and you can move on with your life. Truly. You could start just moving on with your life at that point. And then you'll get like a form of osmosis, if you will. You know, like, you'll be able to absorb and acquire knowledge as you go, and you'll layer it on. There's really two different schools that you could sort of proceed to that point. Your goals, I will say, should determine what you want to do and how much time you want to spend in this stuff. I recommend to just generally understand the concepts we're saying at this point. And if you're studying for the Security Plus, you're probably going to want to start memorizing these things a little bit more and really get them in your head, because you're going to be challenged on them. But then you're going to hop in the field and you're probably going to forget about a lot of these things. And you're just going to generally remember, like, oh yeah, it kind of works that way. Kind of like subnetting. How many of you remember how to subnet fully after we went through it? And don't make me pull up the "be honest" meme. Yep. Kids can build a little stuff on the table. Yeah. Yeah, I mean, if you study for it, you'll be able to memorize it. But yeah, I went through a little module on range force of the day, so it's a little fresh. But yeah, of course. It's the thing of, like, you see, that's the answers I want from you guys in chat, though. Is like, I need a review. I need a refresher. Would have to use it. Yes, perfect, Zeno. Thank you. Use it as reference. That's what you need to remember, is you're going to want to be looking at these concepts as reference. Some of you who will go, and if you're subnetting all the time, for example, and you're like a network engineer, sysadmin, you'll be using it more. But as you generally remember, like the CIDR notation and the subnetting and how you can sort of segment and separate a network, and then as needed and as reference, you move along with your focus area of knowledge, you'll be good. But it doesn't make sense for you to memorize everything. Remember, I'll say this again, because this is an important point to stop and say that. Don't just become a dictionary. People don't hire dictionaries. They hire people that can read a dictionary and then create value with it as needed. They hire people for business solutions and business results. If you try to memorize everything in the book, and that's a bit of an impossible task, you're either going to burn out or not remember things, or over-remember some things that are not important out of bias, and probably struggle with value, and probably struggle working with others too. So you want to focus on what matters. So conceptually at this point in time, what we've had is we've had the TCP handshake happened, whereby Bob and Alice have said, I'm going to start at different sequence and acknowledgement numbers across the room. And then I want to start a secure conversation with you. So what I need from you is I need your ID and I need your public key. So Alice is going to ask Bob that. And I'm going to generate a secret. You're going to generate some secrets. We're going to share them. And then I'm going to generate one more secret and send it over to you on the side that no one can read. And then from here, we're now at the blend. We're now at the KDF, the key derivation function stage. So it's a lot of stuff going on behind the scenes. And what we get is we get this master secret. Because we both have Bob and Alice both have the same ingredients. They put all the ingredients into the blender. They both get the same result. And they have a secret, the pre-master secret, that only they both have as the ingredient. So, part of this, let me ask you then in chat, if I were to hash this input in the blender, should Bob and Alice have the same hash? From start to finish, the whole hash. Good. Good. Good, good, good. Yes. Yes. Yes, they should. They've agreed on the same cipher suite, the same mathematics and the functions. They're going to put all the ingredients in the blender. They're going to get the full hash the exact same way if they needed to. So, what's happening here is this process is going to then yield a couple different things. And you can imagine like this blender is going to pour out into different cups. We've got a couple different things here. We have our keys, we have integrity, and yeah, okay. Trying to remember. Yeah. So a couple things are happening over here. You get this blender now and you kind of pour it out in different cups. And we now have been able to generate a symmetric key, and we've also been able to create a hash. And so this is providing us a couple of things. Confidentiality. And I will also say that this also provides integrity as well too. Or like order, I should say. And a vector, imagine it to just be like a point, like a starting point. When it's called an like initialization vector, that means like this is a starting point of where things are initializing. From here on, we have two different steps that happen. There is a client finished. and server finish message that appear. Back and forth between Bob and Alice. And this is all encrypted. Now. So we'll say this is now two additional steps happen at this point. Both Bob and Alice have been able to generate through multiple functions at this point the final symmetric key. So the public key, the asymmetric exchange that had happened previously over here. Okay. So Alice had generated this pre-master secret. Bob on his end already had a public-private key pair and sent Alice the public key. Alice used the public key to encrypt the pre-master secret and sent that over to Bob. The asymmetric public key exchange finished at that point. From then on, Bob and Alice then go and generate a symmetric key, a shared session key that they're both going to use with the same ingredients, the same blender, the same mathematical functions. They're going to generate the symmetric key, a hash, initialization vector, and a couple other things depending, or more or less. And then from then on, the client and the server, so Bob and Alice are going to send a client finished and a server finished message using this new shared session key that they only both have. And we now have a fully symmetrically encrypted, is that even a word, symmetrically? We now have a fully symmetric encrypted exchange from here on out. That's what's happening when you connect to a website. We have now been able to establish a fully confidential communication, and it's fast because symmetric key encryption is super fast compared to public key. We now have a fully confidential connection between one another. Jordan thinks of the follow as well too. Does that make sense? Generally following? Cool. That's it. That's all she wrote. Now, if you can just generally walk through a recruiter this process and an interviewer, if the questions are asked, this is enough. Like, actually, I should say this is more than enough. If you could even explain like 60% of this, then I think like, yeah, if you could explain like 60% of this, then I think that that's enough, honestly, in terms of like where you're going and we're able to communicate these concepts. Yeah, KS, we covered the Diffie-Hellman exchange. So the Diffie-Hellman exchange is when that pre-shared key was exchanged, and then you established perfect forward secrecy. So kind of going back to, it happened right over here. Yeah. Yeah. That's what that is. The Diffie-Hellman exchange is you create some, like the client random, the server random, you create some information between one another and you agree on a cipher suite. And then one party generates a pre-shared key, in this case, a pre-master secret. One person generates a pre-master secret and then they use the public key to encrypt it. and then they do that exchange back and forth. Yeah. I'll try to do like a high-level recap now as well, too, because I know that's a lot at once, and I'm not going to walk through that all again, but I'll just kind of like list it out, because then the recording you can always review afterwards. So let's kind of walk through this like super high level. Step 1, TCP handshake. Okay. Yeah, recording goes on YouTube, Jordan. Syn plus synac plus ac, and then we have a sequence number and acknowledgement number to establish a sense of order. Step 2, we have the TLS handshake. So this consists of client hello, server hello, client random, server random, yeah, the acknowledgement number and the sequence number, KS. Client random, server random happens after this. There's an exchange. Cipher suites. And then three. This is where we actually get, and public key exchange. Okay. And then we actually get so then we actually get the Diffie, let's just call that, yeah. Diffie Hellman. So client uses public key encrypts a pre-master secret. So let's kind of just recap that area right there. Client sends to server. So that's the client goodbye. Yeah, so that's CI saying, so there's a client finished and server finished at the end of it. So this is what happens. We have the Diffie-Hellman that happens at the end. So like the initial parts, kind of walk through that real quick. So we have a TCP handshake that occurs first. We have the SYN, SYNAC, and ACK TCP flags that are sent back and forth. So it's a 3-step process. Client sends a SYN to the server. Server responds with SYN-ACK. Client responds back with ACK. During this time, they both establish a sequence number and an acknowledgement number that incrementally increase on an agreed upon value, so that now we have an order and a structure and we have reliability. We then enter the TLS handshake. The TLS handshake starts with a couple different exchanges. The client and server both exchange things in the following. Client provides, so client hello comes with a client random, provided cipher suites. A server responds back with a server random, agrees on things, agrees on the cipher suites, and also gives their public key. The client now is going to, the client then is going to use the public key and encrypt what they just generated with all the information that they agreed upon right now, which is the pre-master secret. Once they encrypt the pre-master secret, they're performing the Diffie-Hellman exchange. And the server is going to receive an encrypted pre-master secret from the client. Server can then decrypt it because they have the private key. At this point in time, we now move over towards the end of it, where the client and server both have a pre-master secret, a client random, and a server random. They blend that all together inside of a key derivation function. There's more blending that happens, and they finally generate a master secret. Now, from the master secret, they can derive certain values using more mathematical functions, one of which is the symmetric key. The symmetric key from then on is the key used for all confidential encrypted communication between the client and the server. They also have a hash that they can verify the entire result at this point and trust. They should both be able to calculate the full hash and verify that every step that happened previously from A to Z, from page 1 to the end of the book, is exactly the same. There should not be a difference. And if there is, we have a problem. We also have an initialization vector commonly used, which means we're now going to start at a certain level during this derivation process. We then use, from then on, a client finish and server finish message is encrypted back and forth, and we should both be able to read those messages. If we can't, further something is wrong too. And that's it. That's it. Does that make sense? As much as it can make for a first time hearing a lot of new terms and definitions. Nice. So yeah, KS saying, so DF makes use of symmetric encryption to secure symmetric keys. Correct. This lecture here and all this is probably subnetting is the other major big one, and then understanding this general concept is the other major hurdle. From here on, honestly, you're never going to have something more complex that you run into until you start getting into memory and disk forensics and other really complex things around code, which is far from now. From here on out, everything is going to now get easier, and it's just absorbing knowledge and then absorbing knowledge, reproducing in labs, until you get much more advanced from SOC tier 2 and up, and you start doing more advanced work. And I hope that's reassuring. What's up, and Moad, thanks for the follows. So again, if you can explain what we covered today at a 60 to 70% level, I think that is actually more than good enough. Now, ideally, I want all of you to be able to get through and being able to sort of generally walk someone through this. That should be your ultimate target. Shouldn't be your immediate target. Because truthfully, if you can go and explain these concepts in this capacity, even if you have some gaps, that's fine. Don't worry about it. If you have some gaps, that's all right. I don't have gaps because I've had to explain this many times. And even still, I'm okay, yeah, is it that? Is that? You're still sort of it's not you got to remember as you kind of go. There's a couple different things. I don't expect any of you to be able to explain any of this the first time you hear it. You're going to have to go through it a couple times, work through it, and visually map it yourself. And if you can get, like I said, to a 60 to 70% level, that is actually more than good enough for where you're at right now. And I would be happy if you were to be at that level and then just be able to remember and communicate things correctly and precisely, as opposed to learning something really incorrectly and then thinking that's how it is. Because if you do that, that's actually worse. because then you're actually going to make mistakes in the field and you're going to believe that you were right. And that's not good. So I would rather you just get as much as you can and keep going through it and remember it and then present it and then feel good and confident about those concepts and then just become more proficient with it as you go. And if you can do that, I can tell you, I mean, I've worked with analysts in the field and I know analysts that are in the field that can maybe get through like a 30 to 40% explanation of this if they had to on the spot. I know senior analysts in the field that could maybe get through like a 20 to 40% explanation of this on the spot, and they'd have to reference it as they go. So you see what I mean? Don't fall into the trap of just trying to memorize all this. Conceptually understand it, feel good enough about it, and then you're good. The caveat to that is if you are trying to study for like the Sec Plus and other exams that require you to crunch in a bunch of knowledge to regurgitate and then dump and then not remember it until later, then do that. Yes, like that's clear. You're going to have to go and kind of like stuff this in your head, get to the exam, and then you're going to forget a whole bunch of it as you go, and you're only going to remember it as needed. Cool. Oh, that's a big one. That was one of the bigger lectures. KS, your cryptography exam is coming. This helps a ton. Awesome. That's what I want to hear. Go and crush that exam. Zeno, so how difficult would it be to get the private key from either the client or the server once access is gained to either? Incredibly difficult. You would need to have administrative level to get to the private key. You would have to have the highest level user permission to get to the private key. At that point, there's a lot of other stuff. Karina's asking your bear submit, what was the general purpose of this? The general purpose of this is to understand the cryptographic process of establishing confidentiality between a client and a server, that this happens. And the purpose of it beyond that is going to be, depending on your level in the field, you may be responsible for multiple steps of this process as well too. And in the field, if you are performing triage on, let's say a user downloaded something off of an email, they ran it and it executed some type of command that created a network request to another domain, well, guess what? You're going to be doing a certificate lookup, and you're also going to be looking at the domain and to establish and see, like, does the hash match? Can we ensure that this was like a proper connection or not? And you're also going to look to see if anything was encrypted. You're going to look to see if there was a public key exchange, if there was a symmetric key exchange that happened at some point, to identify, and that'll help you very much inside of your like digital forensics investigations for the chain of custody. As a SOC analyst, what you need to understand with this is what normal looks like. And remember, a SOC analyst looks for things that are not normal. So this is your baseline. And when you're putting out the fire and you're responding to it, you're responding to something that breached some step along this process. And that's how you get a SOC analyst incident or ticket on your board. Something went wrong here and likely is malicious or just tripped a false alarm. So your job is to understand conceptually that this is the flow and be able to identify what went wrong in those steps and then close the ticket. Does that help, Karina? Jordan, I've tried looking. Is there a blue team methodology checklist? I've tried looking at Google as emergency yourself through experience and exposure. There isn't so much like a methodology checklist because, so Jordan, every company is going to have their own preferred, they're called playbooks. So every company is going to have their general playbook to respond to on alerts and incidents, and then they'll create them as they go. There is, however, a competency that you have to have. And we've talked about that on another stream. So if you go to like NIST, NICE, Cybersecurity Workforce Framework. Go to CISA and go to role categories. This is what we make our training off of. Go to protection and defense. Go to defensive cybersecurity or any of these roles. And you should be trying to map yourself. This is effectively your checklist of competencies that you should have to perform work in the field for one of these. Now, our courses are effectively just, we created a course out of this. So our courses train you. I'm not trying to shill here, but I mean, like, if you're looking for a checklist, like, go and look at our curriculum, and that's kind of what we did. This is why we did it. So, like, if you go through, like, our SOC100 curriculum, there's a reason why it covers all of these components. And same with SOC100-2. You go here, and you can see, like, there's GRC, which I just saw there. So recommend risk mitigation strategies. Well, this is why we cover it. Cryptography. This is why we're covering it over here. There you go. Same thing with, like, knowledge of computer protocols, knowledge of cryptographic key management principles and practices. This is why. So we are training you effectively. What you need to first ask yourself, Jordan, is what role are you looking for? Like, are you looking to be a SOC analyst? Are you looking to be a security engineer, a detection engineer, like a threat intelligence analyst, a GRC analyst? And then you should use the CISA website to generate, like, a high-level plan. Like, this is what you want to be able to do, like governance, right? Learn those competencies and find coursework or YouTube videos or streams like us where we're walking you through it, and then absorb the knowledge that way. And yes, this is one of those things that you need to know or be exposed, like Doug is saying. You need to be exposed to this so you understand. So, like, Karina, kind of going back, like, piggybacking on this to give Jordan some reference. If you understand the concept of, like, hashing over here, well, then you're going to understand why when you run, like, a PowerShell commandlet of get file hash, it's going to provide you a hash of a file that you can reliably go to, like, VirusTotal and threat intelligence boards to compare that hash against other people to determine if they've seen that hash in the wild, because you can trust it. And if they've seen that hash in the wild and it's representative of malicious code, then you're going to want to use that hash. But it comes first from understanding the knowledge of the hashing function. That's why we have to have 100% trust and integrity from this perspective of being able to ensure if I run, like, a hash function of a malicious binary, and the hash is like HF13X whatever, I can then go in VirusTotal and, like, look at that hash and see if anyone's found it. And I can trust that if they did, then they've also had the full representation of that binary as well too. Steven's saying, I understand the concepts and willing to use them. I'm curious, are these features built in? What do you mean by that? Like, which features? Yeah. So Steven's saying, yeah, Doug, we'll say it in a moment. I'm wondering how to implement encryption into the lab. Oh, okay. In that case, so Steven, we're going to actually do some labs soon. So we're actually going to be doing a lab after this now of hashing and encoding. We're going to do some ciphers, and we're actually going to do encryptions, and we're going to do, like, a digital certificate lookup. And we're actually going to create our own certificate. So you could do that in your home lab after. You can generate your own certificate and try to sign it. That'll be pretty cool. But yeah, then going back to Doug's kind of thing. So yeah, you know, and this is why I'll kind of use the iPad, for example, too, to kind of show you. So Doug's saying like why would a pen tester or a red teamer or a threat actor go after like the golden keys or golden tickets? Why are they going after this stuff? Well, like, for example, if we... Let's see here. Okay, so for example, right, on step 3 of the TCP handshake, if the golden keys and golden tickets are effectively, and I should say, so like a golden ticket effectively would be like a forged Kerberos ticket granting ticket. And if you can forge a ticket, imagine like going to a club, you're trying to get into the club, and you have a ticket to get inside the club. And it's forged. It's like a fake ID. And all you need to do is just wave the ticket and then you're allowed in. That is much easier for a threat actor. Instead of like, okay, I need to go and like find a crack in the wall and like drill out a hole in the brick and then remove it quietly and get inside the side and take what I want and then reseal the wall and get out. Right? Like that's a lot of work. This isn't like Mission Impossible. We don't want to do that. We don't want to have to like drop from the ceiling with a rope. So if I can get something like the Kerberos, like a TGT, a golden ticket, with like, I don't know, like domain administrator type of like permissions, well, hell, I can just walk in, I can do whatever I want on the network, and I'm going to have full trust. That's why. Similarly, like when we look at this process over here, if I could be a man in the middle and I could start... If I can get in the way of those sequence and acknowledgement numbers and spoof myself to be Bob, and then provide Alice with my own self-signed certificate, well, Alice is going to go and look at my certificate and be like, well, I mean, it checks out. It's signed. And what if the certificate authority was like evilbob.com? But what if Alice didn't check that? How about that? So understanding like how that could happen, and if Alice is if like security controls on Alice's end didn't do a thorough certificate authority lookup and just assumed a level of trust, because let's say Bob was already in the network and our configuration settings weren't set up to go beyond and just did a self-signed lookup and we trusted it. This happens with developers. Developers will go and they're going to create a program like a local web application, and then they're going to sign it themselves on the network as a locally signed service. And then they're going to have the IT team push a policy that says, trust this service so we don't run into any issues. It's fine. We made it. We're okay. Well, here's the problem. If I hop in that network as a threat actor and I spoof my certificate to say that it's signed by one of those already approved local services, which clearly is a lie, well, it doesn't matter. There's a policy in place that's going to trust it. And then I can do whatever I want. And then I can step in this process and I could say, hey, Alice, yeah, send me that pre-shared key. Send it over to me. Yeah, and I'm going to give you my public key. Okay, cool. Now encrypt that piece of data that you want to send my way. And maybe Alice was trying to submit like a credential and they wanted to encrypt it. Well, thank you, Alice. I just impersonated a local development server and I provided everything you were looking for because I know in advance that the IT team was told to approve anything that is signed by that local certificate. Gotcha. This is why it's important to understand these things, how they function, how they flow, because this is what threat actors are looking for. They're looking to see where they could breach trust. Activates trap card. Yeah. Cool stuff. Okay, break time. That was a big one. And then let's actually hop into some labs. So, excuse me. Cool. We're going to go to hashing and encoding. We're going to go Linux. Fire that up. Let's take a little fiber. Refill on energy, drinks, and water. Where's my, there it is, okay. Cool. Nice. All right. Welcome back. Got to set up those buttons on the stream deck now. What's going on in the old chat over there? Bearded, welcome back. Yeah. Hopefully you get to enjoy the recording when you go through it. Yeah, KS and Doug. Yeah, you know what? I agree, yeah. I was thinking about that as well. I think it'd be nicer to have like little community hangouts. Like it doesn't have to be gated behind the SOC100 community. I think everyone could benefit to go hang out together inside of the main Discord channels. And like the course private channels are meant more for like discussing like private content kind of thing. But the sprawl is meant to be like a hangout. Like I'm just gonna go and kind of do whatever, and we can have a couple different hangouts as well too. Like if someone just wants to go play Path of Exile, a little PoE2, have fun. If you want to go and stream it while hanging around Discord, that's cool too. If you want to go and hang out and talk about random stuff, that's all good too. No time to play, Steven? I mean, I applaud that, but at the same time, all work and no play makes Homer go something something, right? Yeah. Yeah, no TV, no beer makes Homer go something something. Yeah. You want to play in real life? Yeah. Yeah, just talk about whatever. Ton of topics. I can't believe you guys went till 2 a.m. Oh, man. 2 a.m. Boom. Yeah, sprawls in the kits. Oh, the list. Yeah. Yeah, so we have the sprawl, meant to just be like a general hangout. And that's cool. Cool. Well, I'm glad you all are hanging out together. Like I said, you can't do this alone. You gotta rely on one another. So, all right, let's dive into things. Let's actually go and do this. Like, we've talked a lot about it. We usually do that when we lead into something big, but let's go and open up our Linux workstation, and we're gonna go and kind of work through the steps of hashing a file. Let's do that. Just for the sake of things, so I don't have to keep tabbing back and forth. So I'm tracking the steps. I'll keep it open on another browser and keep things going along on this one over here. Okay, cool. Oh, yeah, there we go. Took a little bit to load the terminal. Okay, yeah. Hotkeys are working. I thought they were like borked for a moment. Slamming the keys. Okay. Cool. All right, let's fix the resolution as well too. It might be a little bit blurry in the screen, I think. Nice. All right. So, first things first, let's go and let's get some text. So I'm just going to go like echo, this is a sample text file. Damn, Bearded Ruckus, you gifted a tier 1 sub. Wow, thank you. Thank you for the support, and thank you, looks like it landed over to CI. CI, welcome to the Defenders. Thanks for the support, man. This is a sample text file, and let's put this to sample.txt. Cool. All right. So if I go and I run like MD5, I do have it, yeah, MD5 sum, and I'm going to run this on the file itself. So sample.txt. I have a hype train. Nice. Oshi. Thanks for the sub, man, too, as well, too, in the support. I have a limited time to earn emotes. To use emotes. I need to get some better emotes going for this kind of stuff. Cool. Yeah, thanks for the support, guys. Appreciate it. All right, so take a look. So we have this hash over here, right? This is what I was saying. This is what a hash would look like if we run something like the MD5 sum. Actually, we'll do a little what is MD5 sum. So we're going to compute and check in MD5 message digest. So this is another, damn, Baloo, Vinny. Nice. Thanks for the subs, guys. Serious hype train going on over here. I didn't know hashing was such a hot topic. I mean, I can talk hashing all day if everyone starts to sub. I'm kidding. But no, seriously, thanks for the support, guys. Vinny, Baloo, welcome to the Defenders of Level Effect. Thanks for the support, guys. You should have access to a little new emote, which I definitely need to add in some more, but at least you can put in some coffee emotes now. So, all right. Here is what an output of, like, if we run the one-way function against something like sample.txt using the MD5 hashing algorithm, or function, I should say. What this will look like is this is a representative. This is kind of like the eggshell. This is like a shell of the egg. The egg of it itself is sample.txt. And if we were to cat sample.txt, we could see the input. Like, we can actually concatenate the file contents to the terminal. And thanks, Red Mux. KS still wants a black mug. I feel like holding out just for the hell of it. So if we cat this, like we look inside the file, we can see it, right? This is a sample text file. If we run an MD5 sum against it, sample, jeez, if I can type. Cool. This value is like a fragment. It's a piece of the shell that when we cracked it, we threw that egg in the ground and we broke it, it is always, always, always going to be that value. KS, I'll get the swag store done properly soon. I promise. I promise. So if I keep doing this, right? You see what I mean? It is always going to be the same value. In fact, if I copy sample and I call this like copy of sample.txt and I run an MD5 sum against it, guess what? It's the exact same. So what does this tell you? This tells you that the file name doesn't matter, because we talked before about how the file is just representative of a binary value that is stored on the disk. Like physically, the disk has been set in certain ways, which are represented as of zeros and ones when it's powered on, and the computer is just going to read the contents of that file. The file name is just something that kind of sits at the top of it. That's just the file name. It's like a header for the file itself. But the data is what we're concerned about, not the name. So what's in a name? Well, I guess a sample by any other name would be just as much of a sample, apparently, right? And this is how we can do this. This is how we use hashing functions that if I had, like, let's say, copy sample.txt to evil malware, I'm going to say Baloo malware because I know he's in chat over here. Evil Baloo malware dot bin MD5. Take a look at this. So if Baloo had given us some malware that we downloaded over here to get on our system, and it was actually named like sample.txt, well, here you go. You could use the hash to be able to run it like a hashing function against the file, and then maybe I can go look online. I could grab this, and I could go to like VirusTotal and be like, has anyone ever actually seen this hash in the wild before? So if I run it, first of all, it looks like it's getting, we talked about this before, is 0 to 56 on common scanners. Let's take a look at the community. No one's reported it because clearly Baloo hasn't created malware for us. But if they did, well, it'd be a different story. Okay, so let's go back inside the Linux workstation. Now, let's demonstrate what could happen if I mess around with that, actually. That's inside the lab, right? Yeah, let's take a look at the steps. Oh, yeah, that's right. We're going to look at another SHA-256. So here's a more cryptographically secure hashing function in this case. And because it's going to provide us actually a longer digest in terms of size, so it's harder to reproduce and harder to identify patterns, which could be those collisions, and then like the same piece of the shell over and over and over again. So if I were to do sample.txt, we can see over here now that this hash output, like this signature, hype chest open. Oh, cool. Batter up emote. Do you guys have that now? Twitch just told me that. Can you guys use that emote now? This is new to me. Let me know. Yeah, it shows Baloo can use it. Cool. All right, nice. I guess we unlocked a new emote. So thanks for the hype. Hash hype. Hype the hash. Okay. So here's a demonstration that if we were to run an MD5 sum hash function against sample.txt or evil Baloo malware, you can see that a weaker hash function, and we should say weaker in the context of like it'll provide less of an output. So like the bit size is smaller, and as a result, it has less characters that could be used And if it's not a good hashing function, then there's a high chance that it could create a collision, which would mean that maybe it was like, right? So instead of this is not a sample of a text file. Sample2.txt. And if I did an MD5 sum now, let's do MD5 sum sample. 5 sum on sample2.txt. That's not going to work, right? Because it's got to be .txt. Okay, so you can see a fairly small change in the file contents of sample2.txt. Pretty drastic change when we compare the MD5 hash of both of these files now. So small input, drastic output. That's a good sign. But we also have a bit of a concern here because the length is small compared to something like the SHA-256 hashing function, which is effectively, I think, yeah, it's double in size. And that's not necessarily indicative if we have a smaller hash that we're going to run into collisions. It's just an added layer of reliability with the hash. Like, we're going to make a really long hashing function, high bit size, mathematically more difficult to compute, etc., etc. So the chances of the same hash appearing, or like the same pattern that might appear, like, why is this D over here, right? It says D4 and D4 on the exact same spot. So if I was a threat actor, I'd be trying to figure out, like, why did that appear twice? So this is why we try to get some other hashing functions, and that's just something that I'm observing on the spot. That's not in the lab. But if D4 appeared here twice, and I have a pretty similar data compared to the original file, well, I don't know. Maybe D4 is representative of something of like, oh, in this spot or something. Or maybe because they're sort of the same. Okay, so maybe that this DF is representative of having like 6 characters in, right? So like 1, 2, 3, 4, 5, 6, 7. So characters 6 and 7, if that is always is, and I run that again, I don't know. I'm guessing here. I'm just trying to demonstrate like what you might try to do. So echo this is also a sample text file into sample3.txt. And if I were to do like MD5 sum now on sample3.txt, so I'm not seeing D4 there again. So if I was like trying to do some research and analysis here, like my trail ran cold. So that kind of disproved at least that initial theory, or so I think, right? Like maybe I should keep it the same character length or something. Z-Star, thanks for the follow too. So this is how you try to break hashing functions, is you mess around with the input data, the whole data, mind you, you need the whole thing, right? Like I need to consider the entire character length here, capitals, lowercase, spaces, which letter of the alphabet, like all that stuff matters. So if I'm trying to break a hashing function or try to prove that it's insecure, I could look at the math and try to find a mathematical problem. Or if I'm a hacker, I don't care about that, I could just run some scripts that might try to brute force and look for similarities. And I've already identified D4 here appeared twice on a very lightly changed file. To me, that's a little strange. Right? Does that make sense? Kind of like talking about it like that way, of why understanding these functions matter? Let me know. So Zeno's saying, is there a tool hash editor that works similar to a hex editor to show how the data is hashed? Is there a tool hash editor that works similar to text editor? I mean, I mean, there's a couple of things. I guess like you could use something like, you could use CyberChef, which we're going to show. Hashcalc, Hashtool. A hex editor is probably going to be your best bet, and anything that can go in like debug mode. If you were to create a, and this is how these programs work, you could create a program that steps through the computational process of hashing a file, and then you could monitor like the actual memory location. And this is more advanced, but like the stack and the heap and different function calls, and see how memory is being allocated and used and which step it's going through to perform the computation, and then try to recreate that computation and look for like ways to do what I'm doing here really under the hood. Or you could do it like how I'm doing here, high level, and just being like, oh, like this is this, this is that. Bearded says, makes sense. Interesting how you caught that. That's what happens like when you pen test and you red team. Your job is like hyper pattern recognition, looking for things that stick out. And you can only do that when you really start to have a good understanding of like baseline normal. And in this regard, what was I looking for? I was looking for, because if I understand how the hash function works, right? I want a drastically different output from a small change. So therefore, in my mind, I'm thinking right away, I shouldn't see any similar pattern between the two files. So what did I do is I looked for any similar pattern, like kind of comparing them top to bottom. And I immediately, like my eye caught D4 and D4 as a result. So understanding the underlying mechanism of how it works will yield you the ability to look for anomalies. And that's how you become a good attacker and a good defender. But you got to get the definition down. This is why we say like a foundations, right? Like you got to get that foundation nailed down, and understand what you understand and know it well. And you don't need to know it all, but at least you need to know what you need to know well. Okay. So, what else are we going to cover here in this lab? We're also going to cover so Karina's saying, so similar pattern of D4 is not normal. I mean, it could be. So my thinking, like I said, was the hashes should have been like drastically different from a small change. Now, it looks like everything was pretty different, except why was D4 in the same spot? Like, if D4 on the next hash was over here, later on, whatever. But the fact that it's in the same spot and all I did was do a small change, then that made me think, well, cat sample 1... That made me think, okay, well, what changed from here to there? And logically speaking, this remained the same. So if this remained the same and D4 was in the same spot, then maybe there's something here between these values that is likely going to show D4 again. That's why I was thinking that. And I could be wrong, but that's just what caught my eye. So if you like puzzles, cybersecurity is for you. Because that's what it is. It's just a daily puzzle. Yeah, my purpose, Karina, was to see if I could recreate D4 appearing in the same spot. So what I did was I created sample 3, right? And I kept this is in the same spot. Yeah. Never know. I don't know. That's just an example of like, and I mean, I wouldn't do that manually and sit here all day. I'd create a script or like a program to help me through this and like automate that. But this is what I'm looking for. But it comes from a fundamental understanding that the integrity of the file should be the same by reading it from like the first letter to the last character. I'm considering the whole thing. So so by like knowing that, then I know, okay, like this didn't change. But I only knew that because I knew the whole file. So maybe in another life we'll break that that hash. I don't know. But anyways, let's take a look now. And what I'm going to do next, so cat sample.txt. So here's the original file. And what I'm going to do, excuse me, so I'm going to go base64 dash, base64 sample.txt, and I'm going to put this into encoded sample.txt. Okay, so now if I cat this, this is now an encoded. It's an encoded version of the file. And remember, encoding is different than hashing because encoding means I can decode. So the characters of like en and d, these matter. Okay? So if you can n something, then you can D something. That's what that means. This is why we have encrypt, decrypt, encode, and decode. But this is why we have hash, and that's it. We don't have in hash or dehash. Doesn't work that way. So now that we've encoded the file, so cat sample.txt and cat encoded sample.txt. Let's take a look. So here is the original contents of the file. We've now base64 encoded it. And this is just an encoding function. And what this is doing now, it's now provided us a reliable means of transport. If I were to take this and if I were to copy this to you and put it inside of the Twitch chat, you should all go and be able to decode that. And you could do that on the command line or inside on online web apps and do something like base64 code encoded sample.txt. And if you decode it, it comes out exactly the same. So encoding, I mean, it does provide some level of confidentiality, because if you made up your own language, you know, people wouldn't, and you just encoded it, people would have a hard time guessing what it is, right? Wouldn't they? So there's some degree of confidentiality, but it shouldn't be relied upon. Now, something you're going to see is sort of like telltale signs of things. Now, the way that base64 encoding works, and every encoding works a little bit differently, but what it's actually doing is it's encoding input data into chunks of 24 bits, or 3 bytes. So as a result, I'll show you an example. If I were to do something like echo A, and if I were to base64 encode that, well, we can see over here that there is this little equal sign here at the end. And if I were to do echo AA, base64, and all of them have little nuances. But what we're trying to do with base64 is account, and this is where we provide reliability. Base64 will actually append these little equal signs over here to the end of the encoded stream to fulfill that capacity. This is why You might actually have like, so you might see someone say like, oh yeah, that's base64 encoded. And you're like, what the hell? Like, how did they know that? Well, there's a couple different things that could be done about that. Is one, there could be like an equal sign over here. So they know how the function works. And if they saw this towards like the tail end of an encoded string, they'd be like, okay, well, that's base64. That's how they would know. But it comes from an underlying knowledge of how base64 encoding is actually working. So this is something that you're going to be more privy to. You're probably going to see like that equal sign append everywhere quite often. Cool. So Cass saying it's kind of like Morse code. It's not encryption, but confusing enough to not be plain text. Yeah. If something is confusing enough, it could be unintentionally secure as a result. Pretty cool, huh? So this is why, just a little bit of a recap over here. Casting's at an unreleased level effect mug? No, man. But maybe. A level effect mug in the making. Everyone likes the mug all of a sudden, yeah? This is just, it's a fancy Le Creuset mug that I've always wanted, so I ordered one. It's a box. It was on the holiday sale. Yeah, you like the green? It's kind of like Matrix green. Okay. There's an ombre effect. Nice. Okay, I don't know what ombre is. The two of you just said ombre, so I don't know. I need to know what an ombre effect is. Hold on. Ombre effect. Oh, well, how fancy. That's what that means, huh? So we've got, yeah, it kind of, I mean, it doesn't have that like in real life. I think that's just the reflection. Yeah, that's just the reflection of the screen. Sorry, it's not that fancy in real life. If you go to like Le Creuset mug. Here, the classic mug. I mean, I guess it kind of does have like a slight ombre effect. It's a nice mug. Like, it's really like comforting. It has a good weight. It weighs like a pound, and it holds heat well. I did not pay $22 for this mug. No. Hell no. I got this on the holiday sale over here, Canadian. I think it was like 40. It was 40 something for like 4 of them. So I am not spending $23 on a mug. But no, come on. I would never do that. That's crazy. I don't even care if I was rich. I'm not. But if I was, like, I still wouldn't spend $23 on a mug. That's like outrageous. Yeah. Oyster, blueberry, shell pink, artichoke. This is the one I got. I got the artichoke mug. And judging by the fact that everyone is so interested in mugs, I think people need a mental break from today. Too heavy of a stream. Too many heavy concepts. That's how I take that. Artichoke is French for like this type of like, well, here. Artichoke in French. Here you go. That's why. Because we're in Canada. Le Creuset Artichaut. Yep. The name is a hash in and of itself. Yeah. Stone mug. Jordan would rather drink coffee from a bowl. Yeah. I hear ya. Yeah, so is everyone's brains kind of done for the day? Like, if we're this much on mugs, I think it sounds like people need a bit of a break then. I know it is a big lecture. There's a lot to cover today. It's heavy. Heavy. Artichokes are good for you too, CI. Just thought it was cool. Okay. Okay. Taking a color break, coffee break. It's 1:30. We got half an hour left. Let's do a little bit more. Because this is pretty straightforward now that we understand the concepts, right? Okay. Let's go over to lab now. Ciphers and symmetric encryption. All right. So Ariel's ready to go. All right. Question regarding the SOC 1000 series, Jordan. We're in SOC 100, but maybe there will be a SOC 1000 series one day. How much depth is there in each SOC 100? More specifically, the SOC 100-2. You can take a. Yeah, I know. I'm just giving a hard time, Jordan. I know you meant that. Just bugging you. If you actually go to training.leveleffect.com, you can go and take a look at, like, we don't have an ability to do preview yet, but you can open up each module and get a sense from that. You could also go to... I gotta find the curriculum. You go to the training course, SOC 100... The full curriculum is here. So SOC 100-1 has 29 lectures, 79 labs. It's pretty beefy. Plus challenges and quizzes. You can get a look over there. And SOC 100-2 is loaded up as well. Yes, and a certification too. And Jordan, like, you can expect the quality and, like, the depth of how we cover our content is like a stream today. Like, we really want to make sure, like, we're thorough in what we cover and we're targeted. We don't go off track and kind of take you on like tutorial land forever. We keep pushing you. Yeah. Okay. Yes, certifications is what I was thinking, man. So SOC 100 certifications. Yeah, here you go. There you go. There you go. Yeah. All right, let's hop back to it. But yeah, Jordan, hop in Discord, like Cass saying. We can help you out there too. Okay. Ciphers and symmetric encryption now. Let's move over to this lab and talk more about this. This one's a little bit more complex, so it's probably going to be enough to wrap it up. All right. All right. Let's clear that up. So what do we want to do? First things first, let's go and instantiate a little variable over here. We're going to instantiate the plain text variable. This is a secret message. And then if we were to echo this, we can see we've instantiated a variable called plain text. We gave it a value over here. This is a secret message. So that's inside of it. So now one thing we can do is we could do something like a rotation cipher, which we talked about in the theory. So if the moment we take plain text and we alter it with an algorithm, and ideally like a cryptographic algorithm, we get ciphertext, which we could use something like a Caesar cipher, a ROT13 cipher. There are many different types of ciphers that alter and adjust the text. We could also use a simple tool. There's actually the TR tool in the command line, and it allows you to translate or delete characters. So if I were to do something like echo plain text, and if I were to run the translate tool, and I'm saying I want to take anything from A to Z, lowercase and uppercase, I want to shift them. Okay, I'm going to shift them a certain amount of characters forward. A to M, N to Z, A to M. And this is just syntax. Like, this is how you would do it. This is effectively going to shift the character 13 positions like a ROT13 cipher, but on the command line. And we're doing this by using a tool that translates or deletes characters. And you could do this by saying, I want to take A to Z, and I want to move it N to Z. Like the alphabet will now start from N to Z and then go to A to M, and then it'll go from N to Z and start from A to M. So by running this, I've now accomplished, and I've created ciphertext, which turns out to be Guvf if Furberg Zerfinter. It's a new language, by the way. This is now ciphertext because we've applied an algorithm and a basic function in this case of shifting. I apologize to any Germans, but I mean no offense, but yeah, sounds a little German to me. So I actually really like Germany, by the way. Side note. I want to go back. But anyways, we've now applied a mathematical function. We're going to rotate this 13 characters along an alphabet of characters. That's all we've done there. So we've taken plain text, we've applied a cipher on it, which is to rotate it 13 slots or positions on the alphabet, which in turn creates ciphertext. So if I wanted to create a function out of this, let's grab this, Control-Shift-C, and say ciphertext is equal to, and we're going to do some command substitution and evaluation, put inside of the brackets and $sign like we learned back in the day. Now if we... Oh yeah. Ciphertext. I feel like something went wrong there. Let's take a look at that. Why did that... Why did my... What? Hold on. Ciphertext is equal to... Echo plain text, translate, A to Z. Let's do that one more time. Echo plain text. All right, let's do that. Okay. Okay. So, wait, let's do that one more time. Okay. Now, let's do this one more time and see where my problem is. Oh! Should have had a coffee break. Okay, yes. And I should have looked at chat too, because you guys actually even called me out on that. So yes, echo ciphertext. We're not trying to cat the file. Anyways, so yes. What are we saying there as well? Karina is, let me know if this is a rabbit hole. I understand what you're doing, but I'm having a hard time seeing why the first arg translate has 2 range dashes, the second arg has... so Karina, this is just more of like a convention of how the translate command works. So in this case, we're going to translate A to Z, but we're going to actually break it in half and say we're going to start A to Z and then go from A to M. This is how the translate command works. It rotates to this requirement. So once more, like A should be moved 13 positions over to N and so forth. Cool. Cool. Yeah, good. All right. I know. And look, like, again, you don't need to like memorize that. This is just like if I were to go to like TR tool cheat sheet, I don't know. Lower, upper, space. Like it's, yeah, don't get too hung up on like, oh, I need to like memorize how that thing kind of works over there. Just understand that this is just the syntax to perform a translate function to use the translate tool to act like a ROT13 cipher, which we're going to rotate 13 positions along the alphabet. So KS, explain shell. So let's do this. Yeah, it's not that smart though to be able to like give you an exact definition of what this is doing. Honestly, like in this day and age, like I would even recommend to like, I don't know. Yeah, okay. So someone probably has a write-up on it. And if not, like this is a good usage of being able to like go and grab like Gemini or Claude or ChatGPT and be like, all right, because what it's going to do is it's going to be able to break down, it's going to look at the man pages, and don't trust it fully, but it should give you an idea of what it's trying to do, and then you can kind of reference pages as well too. The more we start kind of just using like one-off commands, like after this, you're probably never going to need to use that translate command. Again, it's just to demonstrate the concept at a simple level of how we've taken plain text, ran it through a cipher, and we now have the output of ciphertext. That's really it. Now, it should also be able to work in reverse. So if I were to do something like echo, or rather decoded text is equal to echo ciphertext, translate this backwards now. So we're going to go N to Z, A to M, because this is how it's functioned right now. A to M, N to Z, A to M, and then we're going to set it back to the beginning, like a normal alphabet, no rotations. Oops. Echo decoded text, boom. So cat. Plain text, or rather, sorry. Echo plain text. Echo ciphertext. Echo decoded. So let's just compare to make sure. This looks exactly the same as this. So we had some English, we had some German, we had some English. Perfect. Nice. Make sense? Pretty straightforward, right? This is just like an example of how a cipher works. You would apply a function to it, you get an output, and then you can apply the same function. So this is actually, this is at a very simple level. This is an example of symmetric key encryption happening. The key is 13. Okay? So the key is 13 positions. CI, the semicolon helps run multiple commands. Yeah, it runs each command one after another. Yeah. So this is actually a form of symmetric encryption. It's just not very good. Cool. Cool. So now let's actually work with cryptography. So we're going to actually use the OpenSSL library over here, and this is a library that allows us to use cryptographic cipher suites. Excuse me. This allows us to use cryptographic cipher suites on the command line and for like programming and scripting. So what we're going to do first is we're going to generate an AES key, an AES symmetric key. So AES being Advanced Encryption Standard, and we're going to use the OpenSSL library to be able to achieve that. And this is going to be a complex area because it's a lot of specific commands and cipher suites and language to use at certain times to be able to achieve a desired output. From here on, if any of you students want to get better in this area and do more of this stuff, just be prepared. You're going to be doing a lot of documentation lookups and references of like how to use OpenSSL for certain functions and actually like full on reading the documentation. So we've saved you a little bit of that time in this lab to provide you some of the steps that you can actually walk through it and gain an understanding on your own. So first things first, we need to generate a key. Remember, symmetric is the same key to encrypt, the same key to decrypt. So we're going to use OpenSSL, and we're going to specify rand, so like random. We're going to use 16 hex characters. This is just syntax of the command itself. Key.txt. So this is the key in this case. Now this is going to generate us. We now need to take this key and use it to encrypt a file. So what I'm going to do is first I need some data. Just move the iPad real quick. 1 second. Much better. There we go. Okay. So echo, this is heavily encrypted by 2 to the power of 128. What is 2? Here we go. Something like that. Good luck, hacker. Now I just hope I don't lose the key. Put this into plain text.txt. Okay. So now I have a text file with some super secure top secret information inside here, and I want to go and I want to encrypt this. So I'm going to use the OpenSSL library once again. We're going to specify a cipher suite. And the one in the lab over here, we've gone ahead and we've used AES 128, ECB, electronic code block, code book, electronic code book, ECB. And what that means, because we're not overly concerned about what we're trying to achieve here, it means that identical blocks of text, plain text, should produce identical ciphertext. So it's kind of like a hash in that regard. It's kind of dangerous, because if someone can figure out the pattern, then they could find a loophole. So not recommended entirely. But we won with it for simplicity and speed. There's always a trade-off. Like, the less effective encryption algorithms and cipher suites are also faster or easier to manage, and there's always a trade-off. You can make something super secure to encrypt, like 10,000 bit encryption, but good luck. So, good luck. Yeah, so ECB is generated separately using the same key on the same data. It means same result, correct? Yeah. All what it does is it chops up the input into blocks of sequential ciphertext. But if the blocks were all the same, it would all look the same as well too. So you could slowly unravel patterns that way. So yeah, you're right. It uses the same key. Okay, it's ready to go. So, OpenSSL, we're going to use encode as well. Or rather, encrypt. And we're going to use AES 128 ECB. And we're going to specify the key. And this is just a convention, so cat key.txt. In plaintext.txt, and we're going to do out ciphertext.txt. Super fast. Like super, super fast. But not readable. You see what I mean? So, like, this is what encrypted data actually would look like. Very different than, like, the simple ROT13 cipher we saw above. Now, we should also be able to decrypt this. So let's do OpenSSL. And we're going to specify TAC D, AES 128, ECB, dash key, cat. Something broke over there, hold on. OpenSSL D 128 ECB. TAC in, this time is going to be the ciphertext. TAC out, decrypted text.txt. Cool. Let's make sure. Perfect. Super fast. Like, next to impossible. Like, it's going to be so hard to be able to decrypt that. 10 to the power of 19 years for Hashcat to break that. Yeah. And look how fast you were able to encrypt it and keep it secure. This key that you're seeing right now is similar to, remember when we walked through the key derivation, the KDF, and we generated a shared session key? The shared session key is a symmetric key like this. So you do all of that stuff beforehand to get, like, transfer data back and forth. We're going to do that in next lab. To finally generate a key like this, and now we can encrypt our network communications that fast. That's why we do this. This is why we have encryption. Now, if I needed to pass this encrypted message to someone, I could do something like cat ciphertext.txt, base64, and here you go. I can now package this up into base64 text, and then give this to someone with my key, and they should be able to decrypt it. So if I could do something like this, base64 TAC-D, so we're going to say like base64 encoded and encrypted data. Let's do this. And encrypted data .txt. Okay. And then what we're going to do is we're going to go now and do base64 TAC-D. And we're going to put this into decoded but still encrypted data.txt. We're going to cat that. And you're going to notice, if you can do like a quick visual, you should see that it's essentially the same thing. So like, let's do cat ciphertext, cat decoded, oops, decoded but still encrypted. Oh, that's not going to work. Let's do echo just for a new line for a moment. You can see, like, just kind of visually comparing them real quick. They look exactly the same. So let's go back now to, let's go, whoops. Yes, so here's the decrypt command, and instead of using the decrypted data, I'm going to use decrypted, or rather, sorry, decoded, but still encrypted. Whoops. Oh. That's not what I wanted to do. Okay, I'm going to redo this. 1 second. Because all that I've done over here... Sorry. All I've done is just... Okay. Alright. So let's use our conventions a little bit better, because all I did was just overwrite it. Alright. We're going to go. Base 60... We're going to go back to where we were. Okay. So we're going to go back to this. We're going to redo this together, okay? Alright. So cat ciphertext, base64, and we're going to put this inside of encoded and encrypted .txt. Okay. Now I'm going to base64 TAC-D, encoded and encrypted, and put this into decoded and still encrypted ciphertext.txt. So, cat ciphertext echo. All what I've done is I've base64 encoded the encrypted data, and then I've base64 decoded it. So I'm going to show you what that looks like right now. Decoded. This is not a lab, sorry, I'm just kind of like going cat decoded and still encrypted text. Okay. So again, you can see they're exactly the same. So the base64 encoding encoded the encrypted data and also was able to decode it with 0 loss. That's the function of encoding. To be able to take input like this that is difficult to work with, and you can see it's a bunch of question marks. It's not, you can't interpret it. But I was able to take it and encode it and then pass it somewhere else and then decode it back to its original encrypted cipher state. So now what I want to do is I want to go and I want to decrypt. And what I'm going to use is this new encoded and decoded encrypted text. It's too many words right now. Words are hard. Decoded and still encrypted text, and we're going to change this to a new output file. This is going to be data that was encrypted, then encoded, then decoded, and now plain text.txt. So let's cat that now. And there you go. Zero loss. And this is where you would use something like Base64 encoding with encryption to be able to package up something into a reliable, zero loss, full integrity piece of data that's still encrypted. You can't read it. Send it to someone or something, and then just use simple Base64 decoding. And then it gets back to its original ciphertext state. And as long as I have the symmetric key, I can now decrypt it. And this is effectively what happens with network communications, is you encrypt things and then you encode it with like URL encoding, Base64 encoding, a bunch of others, and then you just send it from client to server, and then when it gets to the other end, you do the decryption. You don't do the encryption and decryption at the beginning. There's usually encoding involved as well too, because you can't transmit this over the wire, at least reliably. Karina appreciates the file names. Yeah, I was trying to give the file names like exactly what it is, so it's explicit. KS. So what do I think? There was a question about what do you now think about quantum computing being able to accelerate break encryption like this? I think we're going to start seeing some form of quantum cryptography. I agree. I think we're going to see more forms of quantum cryptography to be able to create new encryption algorithms. But I also personally believe we will start seeing more reliance on blockchain-related technology to get to a semblance of like Web3, because Web2 is really, really, really a giant house of cards. But there you go. This is in action. This is symmetric encryption with encoding in action. And if we wanted to do something like, we could run like an MD5 sum on the ciphertext and say, okay, cool, this is the digest. Like this is the cipher, this is the hash of the ciphered text that I can rely upon. And if I did an MD5 sum of the data that was this, guess what? Oh, sorry. MD5 sum. I was just like, wait a minute, that doesn't make sense. I want decoded and still. Okay, yeah, that makes more sense. Too many crazy names. Okay, so you see how the hash is exactly the same, even though it went through encoding and decoding. Because it's the same data. This is how I can tell you, hey, I'm going to send you my encrypted text. And when it gets to your end, you can do a hash check on it to be sure that the data from A to Z, from page 1 to 2000, is exactly the same. Because the hash matches. And this is why we have things, let's go back to the iPad. So this is why we have things like with the KDF. This is why at the end we have our symmetric key and our hash. So that we can run a hash check on it too to make extra certain security sure that it's the same file that we're expecting. And also just to share the hash. Without revealing the contents. Pretty cool, huh? This is like this is really amazing stuff. Doug, also what's cool is the character that was reading the Matrix and was the operator. Yeah, his name was Cypher. I know, that was so good. Yeah. Cypher text. And it was Cypher. Nice. Okay, cool. All right. I think that's a good spot. What do y'all think? KS saying, in your class, you did not see any of this? Yeah, like, if you're just studying, like, the books and in school, like, you're not actually going to see it in action like this. This is why we do the lab, so you can just, like, show it. Like, here it is, clearly in action happening, right in front of you. Bearded Matrix movie night in chat one day? You know what? Maybe we'll do a level effect movie night, and we can stream it on Discord or something. Why not? Yeah, it was all concepts, KS, yeah. Karina, big shout out to Bearded and KS. Yeah, these guys are awesome. VIPs, for sure. Yeah, we got a good little community building over here. I like it. Grateful to have you guys over here and, you know, contributing and being engaging, asking good questions, supporting one another. Stuff matters. Our double awesome streams, great to actually do the hands-on. Yeah, 100%. So here you go. I think that's a good spot to stop for the day, though. We'll, so this recording will go up on Tuesday. And we'll see you back tomorrow. Tomorrow, SOC 100. So, once again, thank you everyone for being here today. Thanks for spending your Saturday. Thanks for paying attention to all the deep, heavy concepts. I know this was a big one. But again, thanks for just being here, spending your time, supporting the stream, and helping one another out and asking some really great questions. So again, we wouldn't be doing this if it wasn't for all of you just being here every single day with these streams. So thank you again. We'll see you tomorrow, Sunday, for Windows. Well, we're going to wrap this up. We've got a little bit more to do, and then we're going to finally jump into Windows triage and start looking at ways to triage a compromised Windows workstation. Other than that, have yourself an awesome rest of your Saturday. We'll see you tomorrow.